Hello, friends. It's a beautiful morning where I am. I hope you are doing well. My name is IBM, and I come with another episode of Learning Physics with me. And today, I would like to take you through electromagnetic fields and electromagnetic induction. These are actually there is no clear boundary between the questions of magnetic fields and electromagnetic induction. So sometimes you'll even find questions of alternating current within this same document. So there's no problem with that. After all, alternating current, when we talk about transformers, we shall be actually applying electromagnetic induction. So expect questions which cut across magnetic fields, electromagnetic induction, alternating current, and sometimes questions regarding capacitances. So today I want us to look at solved past paper questions. This is part one. So there will be so many series, there could be as many as 5 for electromagnetic induction. And I hope you'll enjoy this. I hope you'll enjoy this. So let's straight away go to our document where we shall find past paper questions. And this is the document. So the document is attached in a link on the video. So you can always click on the link or copy the link into your browser and try to seek permission for that video. I mean for that document. It is entirely free. So these are the topics we are supposed to study. So I think we have finished. When you check in the links, you have seen that gravitation was recorded, electric fields was done. We also did temperature, ideal gases, and thermal properties. The order of the recorded lessons are matching with my class. So that's why you may not see some of these ones recorded, because maybe like quantum we had done it long time ago, medical we did long time ago, nuclear physics, astrophysics, oscillations we had done it long time ago. And currently we are doing magnetic fields. We have finished SC, but I'll record SC. We are going to move to capacitance, and I will record capacitance. And at the same time, we are studying medical physics with my class, so I will also record medical physics. The other topics which I are not going to be recorded now, it's because I taught them long time ago and we went through these questions physically in class, but I'll still record them later on. But for now, I want to record the ones which I am currently teaching in class. So that's why you may see many topics are not recorded. It's because I taught them long time ago and I did the questions with my class. So I'll record them later on. So let's look for our topic, that is magnetic fields, which is page 160. So I will type here 160. So page 160 is here. We have already reached magnetic fields. It's unfortunate I'm recording this video without internet. Therefore, I will not be able to use the three-dimensional Fleming's left-hand rule model or the right-hand rule model. I would have used it here to show you every time how to use it. But maybe in the subsequent videos, I'll record with the Fleming's left-hand rule and right-hand rule besides my document. Okay, let us start. State what is meant by a magnetic field. So from our lessons of magnetism that you have studied in school or that we have been taught in school, we are now familiar with some of these concepts. The question of magnetic fields will always come many times. Remember, we saw a gravitational field, we saw an electric field, now we should be seeing a magnetic field. We said a field is a region of space where a particle or an object experiences a force. Now this field is specifically a magnetic field. So a magnetic field is a region of space. A region of space where a force or where there is a force produced. This can be by or it can be on. It can be a magnet. It can be a magnetic pole, maybe the north or south pole. It can be a moving charge. It must be moving. It can be a moving charge. It is produced by a moving charge or on a moving charge. It can also be on or by a current carrying conductor. A current carrying conductor. So magnetic pole produces a force due to its magnetic field, or it experiences a force due to its magnetic field. A moving charge produces a force due to its magnetic field, or it experiences a force due to a magnetic field. A current carrying conductor experiences a force due to a magnetic field, or it even produces a force due to its magnetic field. So we can define a magnetic field in any of those forms. Of course, in an exam, you cannot write all these ones. You choose just one. A particle of charge positive q, it is a positively charged particle, mass m, is traveling in a vacuum with that speed. The particle enters at right angles a uniform magnetic field of flux density B as shown here. So the particle is entering from the bottom. And you notice that the circular path has its center almost towards this point. So that means the force is always acting towards this point. The force is acting perpendicular to the direction of motion of this particle. That's why it is causing centripetal force, so that the particle moves in a semicircular arc. So state the direction of the magnetic field. So we have now predicted that the force must be towards this point, towards the center of the circular path, but the particle is moving in this direction. So this is already 90 degrees. So by Fleming's left-hand rule, your thumb should point towards this side, that is towards the center of the circular path. And the second finger, which is supposed to be, remember from Fleming's left-hand rule, the second finger must point in the direction of current. But current flows from positive to negative. That means the positively charged particles move in the same direction as current, conventional current. So hold your left hand rule with the thumb, the first finger, and the second finger at 90 degrees. Make sure the thumb points towards the center and rotate your second finger to point in the same direction as the particle. So the second finger should point in that direction. When you try to do this with the second finger pointing in that direction, you will notice that the first finger will be pointing just above your paper, that is out of the plane of the page. So if you make the thumb to point to the left, I mean to the right, towards the center, and the second finger, which is the one which shows current, pointing in that direction, you're going to see that the thumb is above the paper. It is coming, the thumb is pointing, I mean the first finger is pointing out of the paper. It is easier. If that is hard, you can still use Fleming's, you can use Fleming's right hand rule if you are an expert on doing this. But for Fleming's right hand rule, it would mean again you have to reverse the second finger to point downwards. The thumb pointing towards the center, the second finger of the right hand pointing towards, it will now be pointing towards you when you are facing the question paper, because you must reverse it for a positive charge. If you use the right hand, you reverse it for the positive charge. If you use it for the negative charge, you don't reverse the second finger. If you use the left hand, you reverse the second finger for a negative charge, but you don't reverse it for a positive charge. So it is always easier to use the left hand and be consistent with it. Alternatively, you can put the question paper above your fingers. It is easier that way. With the thumb pointing to the right hand side or towards the center, and the second finger pointing away from you, you notice that the thumb will be pointing upwards. That means using Fleming's left hand rule, the field is actually out of the page. So it is out of the plane of the page. or that is out of the plane of the paper by Fleming's left-hand rule. Similarly, even if you use the right-hand rule, it will give you the same thing. But using the right-hand rule, you should be an expert. And note that the left-hand rule works directly for the positive charges. The left-hand rule still works for the negative charges, but with the second finger being reversed to be in the opposite direction to the direction of motion of the particle. The right-hand rule works directly with negative charges without reversing any fingers. But when you use the right-hand rule for positive charges, again, you make the second finger to point in the opposite direction. That is the logic behind that. Explain why the speed of the particle is not affected by the magnetic field. So you notice that the force is acting towards the center. This is the force due to the magnetic field, and this is the direction of the velocity. So you notice that the force is always perpendicular to the velocity or to the direction of travel. So there is no work done by the force on the particle. Therefore, the acceleration is always going to be perpendicular to the velocity. So the force on the particle, is always perpendicular. Is always perpendicular to the velocity or to the direction of motion. To the direction of motion or the direction of travel. So there is no work done. No work done by the force on the particle. And since there is no work done on the particle, then the speed of the particle is not affected, because the speed will only be affected if the force does work on the particle. So we simply say the acceleration is always perpendicular to the velocity. That is because the force on the particle is always perpendicular to the velocity. Remember, force is mass times acceleration. These two vectors should always be acting in the same direction. So since the force is always perpendicular to the velocity, the word always here is very important in the magnetic field. The acceleration is also always perpendicular to the velocity. Therefore, the speed is not affected by the force acting on the particle. Show that the diameter d of the semicircular path is given by that expression. So when the particle enters a uniform magnetic field, the magnetic force on the particle is causing it to move in an arc of a circle. Therefore, we say the magnetic force provides the centripetal force. So the force due to the magnetic field provides the centripetal force, which I'll call Fc. That means BQV should be equal to mv squared over r. And when you remember the radius is equal to the diameter divided by 2. So we are now going to substitute. Of course, 1v has cancelled. So we now have that BQ is equal to mv divided by, where there is radius, I'll put diameter over 2, so that is d over 2. And this simplifies, the 2 goes up, it becomes 2mv divided by d. So that means, therefore, that when I make d the subject, I now have that BQ is equal to twice mv divided by d, which simplifies to d equals to twice mv divided by BQ. Use the expression in B to show that the time Tf spent in the field by the particle is independent of its velocity. So we know that time is distance over speed. So time is going to be equal to distance divided by speed. So the distance is going to be actually the circumference. It is a semicircle. So the distance is the circumference of the semicircle. And we know that circumference is pi d for a full circle. If it is half a circle, it will be pi d over 2. That is the circumference. So the time tf is going to be the distance, which is pi d over 2, then divide by the speed, which is v. So this is actually pi d over twice v. When I substitute for d, which is in the previous part here, so I have that pi divided by twice v times d, which d is twice mv, divided by bq. And you realize that 2v has cancelled, and this means that tf, the time tf, is equal to, I'm remaining with the pi times m, that is pi m divided by bq. So you notice that it is independent of, v. It is independent of v because v is no longer in that expression. Okay, state Coulomb's law. At this point, we are now familiar with Coulomb's law. So we know that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of the separation. So I'll simply say the force. Because they have already referred to 2-point charges, I'll simply say that the force is directly proportional. To the product. Of the point charges, that is their magnitude, and inversely proportional to the square of their separation. So that is Coulomb's law. Whenever you are stating Coulomb's law, make sure you refer to point charges to get full credit. The force between 2-point charges is directly proportional to the product of the point charges and inversely proportional to the square of their separation. So that is Coulomb's law. 2-point charges are situated in a vacuum and separated by a distance r. The force between the charges is Fc, that is the maximum force between the charges. Sketch a graph to show the variation of the force F between the charges with the separation x, for values of x ranging from xr to 4r. So when the radius is r, the force is Fc. So note that the force, we have already seen there that the force is equal to, so I remove that, will be a constant. The product of the charges, say q1 and q2, divided by r squared or x squared. I'll say divide by x squared. We have seen that when x is r, this force here, which is going to be k q1 q2 over where there is x, I put the r squared, this force is given as Fc. Let's check when the distance is 2r, the force at 2r is simply, we just replace x, so it will simply be, when I put here r 2r squared, it becomes 4r squared, so the force becomes a quarter of Fc. For 3r, F3r is going to be equal to, I put here 3r squared, it becomes 9r squared, which is 1 over 9 of Fc. When I check on 4r, the force at 4r is going to be equal to, I put here 4r, when I square it, it becomes 1 over, it becomes 16. So this will be 1 over 16 of Fc. So all we need is to find a scale. So our graph will start from this point here at the surface, when when the distance between the two is r. So all we need is to find a scale here. We get 0.2 divided by the number of small squares. So the scale is 0.02. So now, if I want to sketch a quarter R, a quarter of FC, I know a quarter, I will just get to a quarter divided by the scale 0.02 to get the number of small squares I need to look for when I'm plotting against 2R. So a quarter, that is 0.25 divided by the scale 0.02. So I will count, this one gives me 12 small squares, 12.5 small squares. So I will count 12.5 small squares from the bottom to get where a quarter FC would be exactly. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. So this is where I have a quarter FC. Then I check for 1 over 9. I repeat the same. 1 over 9 divided by the scale on the vertical. So 1 over 9 divided by 0.02. I'm getting 5.6 small squares. So I'll just count approximately 5.5 or 5 or 6 small squares. So this is 1, 2, 3, 4, 5, 6. So 5.5 could be around here. So that is 1 over 9 FC. Then I check for 1 over 16. So I get 1 over 16 divided by the scale. The scale is 0.02. So these are 3.125 small squares. So that will be approximately 3 small squares. So I will count 3. 1, 2, 3. So 1 over 16 is around there. So I have 1, 2, 3 points plus this one. So my graph will be a smooth curve through those points. So it is not easy to draw this on computer, but for using a pencil, you can draw a very nice smooth curve. It shouldn't be a line, it should be a smooth curve. Something like that. Extremely smooth, going through the points that you have plotted. Mine may not be very accurate because I'm drawing on a computer. So for yours should be very accurate. At least the shape will be the same, and I've showed you how you exactly plot those points. Okay, next. Two coils C and D are placed close to one another as shown here. Of course, if we close the switch, if this is alternating current, unfortunately it could be direct current. You notice that if current is flowing in this direction, if you tried to use the right hand grip rule, you fold your fingers in the same direction as the current, the fingers will be pointing upwards, and your thumb will actually be pointing to the left. Therefore, using the right hand grip rule, this will be north, the other one will be south. And if Y was to use Lenz's law, this will be, actually here the field is in this direction. So therefore, by Lenz's law, the field here will also be in that direction, where this will be south, the other one will be north. And again, if I was to use the right hand grip rule, grip the conductor, assume you are gripping the coil in your hand with the thumb pointing to the north. Your fingers will be folding downwards, so the current here, the EMF here, or the current here will be in this direction here. That is just a by the way, it may not be part of the question. Just to remind you of Fleming Lenz's law and how we come up with the direction of the induced EMF or current and so on. But the variation with the time t of the current I in a coil C is shown in the figure here. On the figure 5.4, show the variation with the time t of the EMF E induced in the coil D for time t equals to 0 to time t equals to T5. Now remember, according to Faraday's law, an EMF is induced whenever there is a change in a magnetic flux linkage. So EMF is equal to N times change in flux with time. And flux only changes when the current is changing. That's when the magnetic field will be changing. And therefore, whenever the current is constant, then the flux is also going to be constant. The flux linkage is going to be constant. And if the flux linkage is constant, therefore there is no induced EMF. So I am saying when the current is not changing, the flux linkage is constant. And it is only going to change when the current also changes. So what does that mean? It means that between t equals to 0 to t equals t1, where the current is constant, here the EMF induced is 0, here the EMF induced is 0, and here the EMF induced is 0 because the current is constant. Therefore, on this graph, between t equals to 0 to t equals t1, I will draw a horizontal line along the x-axis. I will draw, let me increase the thickness of this line. So this is going to be a horizontal line along the x-axis. Again, between we have seen between T1, T2 and T3, the current is still constant. So this will also be a horizontal line along the x-axis. We have also seen that between T4 and T5, the current is constant. This will also be a horizontal line along the x-axis because the EMF is 0. Whenever the current is constant, there is no EMF induced. Therefore, that will be represented by a horizontal line along the x-axis. But then, between t equals to t1 and t equals to t2, there is a change in current. And between t equals t3 and t equals t4, there is a change in current, but these two are in opposite directions. That means between t equals t1 and t equals t2, the change in current will be in opposite direction to that, or the EMF must be in opposite direction to that between t3 and t4. But how will we find that magnitude? Note that on the vertical, they never gave us anything like marks or a scale. So we shall just use the number of boxes. Note that the EMF is going to be directly proportional to the gradient. So because the gradient is directly proportional to the rate of change of magnetic flux. So the EMF will be directly proportional to the gradient. So I will rely on the gradient to tell the exact magnitude of EMF. Note that the lines are straight, so the gradient is constant. Therefore, the EMF represented between T1 and T2 will be constant value and not 0. So let us find these are 10 small squares from here to here plus another 10. So the gradient there is on the vertical is going to be 20 squares divided by on the x-axis from T1 to T2 there are 5. So the gradient is represented by 20 over 5, which is approximately 4 squares. Those are approximately 4 squares representing the gradient. Let's check this one. On the vertical from here up to here is 20 plus 10, that is 30 squares. So we have 30 squares over, these are 5 squares. So the gradient is actually going to be 6. So these were 5 squares, 30 squares. So that is 6. Let me wrap off this. So as somebody who knows mathematics, you must know that 6, not 4. 6 is the same as 1.5 times 4. 6 is the same as 1.5 times 4. That means if I represent a certain number of, I use a certain number of squares to represent this gradient here. On them, I will add 0.5. I will add half of them to represent 6. So if I say the current here is the EMF here is represented by 10 small squares, then the EMF represented here should always be 1.5 times the EMF represented here. So 1.5 times 10 squares, that is actually 15 small squares. So I'm now looking for 10 small squares here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember, the gradient is constant, so the EMF is a constant value. So this is going to be the EMF here. So I'll just do a step like that. Then for this one here, because the second gradient is 1.5 times the first gradient, remember they are in opposite directions from here. This is a negative gradient, the other is a positive gradient. So just put them on opposite sides. Even if I put this one at the bottom and the gradient, I can put this one at the bottom and I put this one at the top, there's no problem. As long as they are in opposite directions to show that the EMF changed direction. So here I will represent this with the 15 small squares because I've represented this with the 10 small squares. So I will draw this one. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12, 13, 14, 15. So this will be here. So using a ruler, you can draw very neat steps. Using a ruler, you can draw extremely neat steps. So that is going to be our graph. We don't just guess it. We actually used the gradients to be very accurate and draw something which is accepted. Okay, so let's proceed. Let us proceed. A thin slice of conducting material is placed normal to a uniform magnetic field of flux density B, as shown here. So the magnetic field is normal to face C, D, E, F, and to face P, Q, R, S. A current I passes through the slice and is normal to the faces C, D, Q, P, and F, E, R, S. A potential difference, the whole voltage, is developed across the slice. State the phases between which the whole voltage VH is developed. So even here, we are going to use Fleming's left-hand rule. If I have a charged particle which is positive in here, because the current is flowing in that direction, so the particle is, due to the magnetic field, the force due to the magnetic field is vertical downwards. I mean, the magnetic field is vertical downwards, so the first finger points downwards onto the slice. But because the current is going the other way around, the other way, the second finger points towards the other end, the second finger points towards that end. When you place your first finger on your paper and rotate the second finger to point in that direction, you notice that the thumb on the positive charge will be in that direction. That means the positive charges are accumulating this side. When you again press your first finger onto the paper, and then make sure that the second finger points in the opposite direction, because we are now looking for negative charges. For a negative charge, you reverse the second finger to point in the opposite direction to that of current. So when you put your first finger onto your paper to represent the field onto the paper, rotate your hand for the second finger to point downwards in the opposite direction to current. Your thumb points this side, meaning that the negative charges are coming this side. Therefore, the positive charges are accumulating on the other end, with the negative charges accumulating on this end. That means the PD is set up across the two opposite faces. Therefore, this will be D, E, R, Q, and the other side is P or C, F, S, P. Those are the faces between which the whole voltage is set up. The current I is produced by charge carriers, each of charge positive Q, moving at a speed v in the direction of the current. The number density of the charge carriers is n. Derive an expression relating whole voltage V, B, and D. So note that when the whole voltage is set up, the force due to the magnetic field is equal to the force due to the electric field. Of course, as the whole voltage is set up, on the other side, there will be a positive potential. On this side, there will be a negative potential. There is a potential difference between the two ends. That potential difference creates an electric field. Therefore, a charged particle in here, a charged particle here, is now experiencing a force due to, if the particle is positive, it is experiencing a force due to the magnetic field towards the other end, and it is experiencing a force due to the electric field towards this side, because there is already an electric field which has been set up. When the two forces balance, the particle cannot move to any side, so the potential difference stops growing. Therefore, the force due to the magnetic field is BQV on the charged particle should be equal to the force due to the electric field, which is Q times E. And this means, because Q cancels, V is going to be equal to E over B. But we want in terms of VH. So we know from electric fields that electric field strength can be given as V over D. Now this is going to be VH. So what is D? The distance between this face and the other face is going to be actually the D, the value of D. These two ends will act as if they are opposite, they are poles with opposite polarity. So their separation is going to be D. So this means E is VH. Now I'm simply substituting or simplifying here. So it means VH is the same as E times D. Yet from this expression here, we also have that E is also equal to V times B. So we just combine. So VH is going to be, where there is E, I will put there V times B, then times D. Or precisely VH is equal to B V D as required. Okay, so what is very important is saying that the magnetic force, when the whole voltage is set up and it is constant, the magnetic force is equal to the electric force, which due to the electric field which has been set up. Okay, use your answer in B Roman 1 and an expression for the current I in the slice to derive the expression VH is BI. So one, we know that using from AS content, we know that current is equal to NQVA. Sometimes many of my students want to just say never, where E is the charge of the electron, but it may not always be an electron. That's why I prefer to use NQVA. N is the charge density, the number density of the charge carriers. Q is the charge of the charge carriers. V is the drifting velocity. And A is the cross-sectional area of the conductor, where A in this case is going to be the thickness of the conductor times D. So we come back here. A is the cross-sectional area is this part here, or the other part there. So the thickness from here up here, dq is the thickness, which is T, and the distance between the one face to another face is D. So the cross-sectional area is going to be T times D. And therefore, if I make V the subject here, because in this expression we don't need V, we notice that V is going to be equal to I divided by NQ. Where there is A, I am going to put there T times D in that expression. In this expression where there is A, I'm putting TD. Now I simply go back and substitute from whole voltage VH. VH is equal to B V times D. I'm now substituting to become B. Where there is V, I'm putting there I over NQT times D, then times 1D there. Of course, D has cancelled, and this gives you the expression which is required, that is BI divided by NQT. Okay, so we have actually showed the expression required. Suggest why the whole voltage is difficult to detect in a thin slice of copper. A thin slice of copper. What do we know about copper? Copper is a metal, and we notice that whole voltage VH is inversely proportional to N. Now, when they say thin slice of copper, I know most of us will concentrate on the thin part. We shall not concentrate on the copper part. And I know when they say thin, they are saying it is difficult to detect. And again, they are saying thin, yet you can see VH is inversely proportional to T. But when they talk about copper being a conductor, it is a pure conductor, it is a metal. we notice that from VH equals to BI divided by NQT, we see that the whole voltage VH is inversely proportional. So the whole voltage VH is inversely proportional to the number density. The whole voltage is inversely proportional to N. In metals like copper, in metals like copper, in metals like copper, N is very large. N is very large. This is because VH is inversely proportional to N, and N is very large, then it means it will give a very small value of VH. So N is very large, giving a very small value. Giving a very small value of VH. That is for the copper. N is very large for all conductors, pure conductors, all metals. And we are seeing that VH is inversely proportional to N. N, remember, is the number of charge carriers per unit volume. It was defined here. The number density of the charge carriers is N. Number of charge carriers per unit volume of the conductor. Okay, so we are saying VH is inversely proportional to N. In metals like copper, N is very large, giving a very small value of VH, which is difficult to detect. Which is difficult to detect. Note that whenever you take a small measurement, you introduce a large percentage uncertainty. Therefore, if n is very large and the VH is very small, then the percentage uncertainty is very large. Okay. A thin slice of conducting material is placed normal to a uniform magnetic field as shown here. The magnetic field is normal to face CDEF and to face PQRS. That means the whole voltage must be now created on the other opposite sides, CPFS and DQRE. That is where the whole voltage will be created straight away. You see that, because I have showed you that if we consider a positively charged particle, the field on it is downwards, the current is in that direction. So the second finger points in the direction of current. The first finger points onto your paper. If it is on table, make the first finger to point onto the paper. Rotate the hand so that the second finger points in that direction. You see that the thumb points towards that side, meaning that a positively charged particle is being dragged to this end. So this end will be positive. The positive ions will accumulate on that side. Similarly, the negative ions will accumulate on this side. If the particle is negative, put your first finger onto the paper if you have it on paper, and rotate the second finger to point in the opposite direction to current. You notice that the thumb points this side. So it means the negatively charged particles are accumulating on the other side. So they said state the phases between which the whole voltage is developed. That is actually going to be D, E, R, Q, and C, F, S, P. The order does not matter. The order of the letters does not matter. Okay, explain why a constant voltage VH is developed between the phases you have named. Why is it a constant value of VH? Why doesn't it grow up to infinity? Why doesn't the PD between this side here and the other side become or grow up to infinity? Why do we have actually that whole voltage? Number one, the charge carriers are actually moving, and they are moving normal to the magnetic field. When the charge carriers are moving normal to the magnetic field, they experience a force due to the magnetic field, which drag them on either sides depending on the charge or the polarity of the charge. And by Fleming's left-hand rule, we can tell the direction on which the charge moves. So there is what we call charge build-up. Charge accumulates on these sides. It builds up. That charge which is building up on the opposite faces is creating an electric field. An electric field will give rise to an electric force which balances with time, balances with the magnetic force. At that point, the potential difference between the two faces remains constant. Therefore, we are saying that the charge carriers are moving normal to the magnetic field. Charge carriers are moving normal to the magnetic field. Charge carriers are moving normal to the magnetic field. These charge carriers experience a force. The charge carriers experience a force normal to the current. Normal to the current and the magnetic field. And the magnetic field as suggested by Fleming's left-hand rule, or as given by Fleming's left-hand rule. As given by Fleming's left-hand rule. So this charge build-up results in a PD across the slice. This charge build-up results in a PD, that is a potential difference across the slice, across the conductor, which sets up an electric field. Which sets up an electric field across the slice. So when does the charge stops building up? The charge stops building up when the force due to electric field balances with the force due to the magnetic field. So we shall simply say that the charge stops building up. The charge stops building up when the force due to the magnetic field which was already there is balanced with the force due to the electric field which has been created in the process of charge building up. And at this point, a constant voltage is established. So that explanation is what will give you 4 marks. Charge carriers, of course, in the conductor, the charge carriers are moving normal to both the current and the magnetic field. In other words, they are actually moving on the opposite faces. And this is in accordance with Fleming's left-hand rule. These charges build up on the opposite faces and the PD is created across the two faces. This PD gives rise to an electric field which creates an electric force on the charge carriers. So the charge build-up will stop when the force due to the electric field is balancing the force due to the magnetic field which was already there. And we said a constant voltage VH is going to be established. Okay. So two slices have similar dimensions. One slice is made of a metal, and the other slice is made of a semiconductor. For the same voltage values of magnetic flux density and current, state which slice is either, if either, will give rise to a larger hole voltage. Explain your reason. Of course, we have noticed that the hole voltage VH is equal to BI over NTQ. They have the same dimension, so we don't expect the thickness to affect. The only thing which will affect, the current is the same, B is the same, or if the charge carriers are the same in magnitude, then we are now noticing that VH is inversely proportional to N. VH is inversely proportional to N. So now, number one, we note that VH, that is the hole voltage, is inversely proportional to N. The hole voltage is inversely proportional to N. Remember, N is the number density, or the number of charge carriers per unit volume. Number density of charge carriers, that is N. So the hole voltage is inversely proportional to N, and N is smaller in a semiconductor. N is lower or smaller in a semiconductor. N is smaller in a semiconductor, so VH is larger for a semiconductor. N is lower or is smaller in a semiconductor, so VH is larger for a semiconductor. We have seen that for a metal conductor, there is a large value of N, that is the number density of charge carriers is larger in pure conductors. And if the number density is larger, it means VH is smaller and difficult to detect. That's why there will be a larger hole voltage in a semiconductor than in a metal. VH is inversely proportional to the number density of charge carriers. Note that N is number density. Number density of charge carriers. That is N. State what is meant by a field of force. A field of force, this is a region of space. Region of space. Region of space where an object, it can be a particle. Region of space where an object or a particle experiences a force. A region of space where a particle experiences a force is what we are calling a field. Bear with my handwriting because writing on the computer is too hard for me. So a field is a region of space where an object or a particle experiences a force. That is a field. It can be an electric, magnetic, or gravitational field. Explain the use of a uniform magnetic field and a uniform electric field for the selection of the velocity of charged particles. That is now a velocity selector. You may draw a diagram if you wish. Many times when they say you may draw a diagram, in fact, the diagram is always the easiest to reduce your explanation. So I will summarize this in a diagram and I will just explain this in words so that maybe because the space is not enough for me. But in one, I know this question appears many times. When the space is large, I will elaborate it in more details. So one, uh, I need an electric field, so I will draw two parallel plates. Let me say one is positive and the one at the bottom is negative. I am going to consider a positive charged particle because I have to make sure that my fields are in the right way, they are in the right direction. So I'm going to consider a positively charged particle coming into the field. That means when the particle enters the field, it will be experiencing a force due to the electric field which is downwards because the particle is positive. So the force due to the electric field is going to be downwards. I'm calling it Fe. Then I am going to introduce a uniform magnetic field in the same region. So I am introducing a uniform magnetic field in the same region. Uniform magnetic field, I will put it into the page because I want the force to be upwards by Fleming's left-hand rule. I'm not just guessing, I want the force to balance Fe. For the force to balance Fe, the field should be into the page. So this is B field into the page. When I write B field, that is the magnetic field. So we use a cross to show that the magnetic field is into the page, which means that the force due to the magnetic field using Fleming's left-hand rule, the first finger pointing onto your page, the second finger pointing in the direction of the velocity, you notice that the thumb points upwards. Try that on your paper, question paper. The first finger onto the paper, the second finger in the direction of the velocity of the charged particle, the thumb is pointing upwards. That means when this particle enters the crossed field, the force due to the magnetic field is upwards. I'm calling it FB. So we shall simply say, without even putting anything else, I'll just draw the path to be that. And I will simply say in my writing, the electric field and the magnetic field are normal to each other, and the velocity of the particles of the velocity of the particle. So because I want to put much writing here, I drew a small diagram. So I am saying the electric and magnetic fields are normal to each other and to the velocity of the particle. This can also be verified from the diagram. That's why I told the diagram simplifies a lot of things. The magnetic force and the electric and the magnetic fields are normal to each other and to the velocity of the particle. The forces on the particle are in opposite directions, as you can see from the diagram. The forces on the particle are in opposite directions, as you can see. Lastly, the fields are going to be adjusted. The fields are adjusted so that the forces are equal. So that the forces are equal such that particles with speed particles with a particular speed. I don't know why my handwriting is bad these days. So such that particles with a particular speed, that is V equals to E over B, are selected. By the way, when I draw this diagram, very neat diagram. If I was to draw this very neat diagram, I put all these. I just state one statement that the fields are adjusted so that FB is equal to FE, and velocities with the speed V equals to E over B are selected. As simple as that. All this theory, this writing here, is only because I wanted people to know what I'm talking about here. But when I draw a neat diagram, the diagram here gives me around 3 marks. Just writing one statement that the fields are adjusted so that the forces are equal, such that particles with a particular speed or particles with a speed v equals to E over B are selected, would give me all the marks. So just note that. A beam of charged particles enters a region of uniform magnetic and electric fields as illustrated here. The direction of the magnetic field is into the plane of the paper. Into the plane of the paper. So into the plane of the paper, that is something like that. So the first finger must be pointing onto your paper. The particles are positively charged. The second finger must be pointing in that direction. A particle in the beam has mass m, charge q, velocity v. The particle passes undeviated. That means its value v should be equal to E over B according to the velocity selection. On the figure, sketch the path of a particle that has mass m, speed v, charge 2q, velocity v. You notice that if the particle has velocity v, then that particle will always be selected and deviated, because the speed v, the selection is not depending on the mass, is not depending on the charge, as long as the velocity has remained the same. Therefore, for the particle q, I will draw a horizontal line along the original path. So I'll just draw a horizontal line along the original path. Particle q will also take that path. So I will label this the path for particle q. They said label this q. Then mass m, charge positive q, and the velocity slightly larger than v. If the velocity is slightly larger than v, what does that mean? The new velocity, which I'm going to call velocity prime, is greater than v. In other words, it is greater than E over B. What does that imply? If you equate BQV, if you say BQV is greater than EQ, you will notice, or you will realize that actually the new velocity V prime being greater than E over B implies that the force due to the magnetic field is greater than the force due to the electric field. That's what it implies. If the new velocity is greater than the initial velocity, it means that the force due to the magnetic field is now, is now higher than the force due to the electric field. So let's verify in which direction is the force due to the electric field. Here they said we have a region of uniform magnetic and electric fields, and the direction of the magnetic field is into the paper. That means using Fleming's left-hand rule, the first finger onto the paper, the second finger going to the right. The first finger is onto the paper, the second finger going to the right. The thumb points upwards, meaning that the force due to the magnetic field is upwards. So therefore, the force due to the electric field must be downwards. So it means the particle, because we are seeing that FB is now greater than FE, the path of this particle should be upwards. Therefore, I will draw a smooth curve. Of course, you will draw a very smooth curve. Me, it is very hard on the computer, but I am trying. So the particle will take that path. So this is going to be labeled a V, path capital V. Because here, the new velocity V prime is greater than the first velocity. Okay, next, an electron having a charge An electron having a charge negative q and mass m is accelerated from rest in a vacuum through a potential difference V. The electron then enters a region of uniform magnetic field of flux density B, as shown in the figure below. Okay, so we can see the figure, it is an electron. The direction of the uniform magnetic field is into the plane of the paper. So the magnetic field is into the plane of the paper. The velocity of the electron as it enters the magnetic field is normal to the magnetic field. Okay. The radius of the circular path of the electron in the magnetic field is r. Explain why the path of the electron in the magnetic field is the arc of the circle. So here, using Fleming's left-hand rule, you are going to notice that the velocity, the magnetic field, and the force are always perpendicular to each other. So the force remains constant, therefore it does not also change the speed. And since it does not change the speed, it simply provides the centripetal force. So we shall simply say that the magnetic force is constant. The magnetic force is constant and always perpendicular or normal to the velocity or normal to the direction of motion. Normal to the velocity, or call it the direction of motion. The magnetic force is perpendicular and is constant and always normal to the velocity or direction of motion. So the speed remains constant. So the speed is constant. In other words, kinetic energy remains constant because the speed is not changing. In other words, we say that there is no work done. No work done. So in other words, the force is not doing any work. Therefore, we simply say that the magnetic force just provides the centripetal force. So the magnetic force just provides the centripetal force. It doesn't do anything else. It doesn't do work. It doesn't change the kinetic energy. It doesn't change the speed. So it just provides centripetal force. Therefore, the particle will be compelled to move in a circular path. Show that the magnitude P of the momentum of the electron as it enters the magnetic field is given by that expression. So when it enters the field, it is actually going to be losing because they say the direction of the uniform magnetic field is into the plane of the paper. The velocity of the electron as it enters the magnetic field is normal to the magnetic field. So because the velocity does not change, of course, when it is just entering, there is a change in it had kinetic energy, if I'm to put it like that, which is now going to become potential energy when it is actually in the field. Or when it is being accelerated towards the field, it has potential energy which is given to it by the accelerating PD. So it loses potential energy and it remains with a constant kinetic energy in the magnetic field. So we can say that the loss in potential energy of the electron as it is being accelerated to enter into the field is equal to the gain in or the increase in kinetic energy before the electron enters the magnetic field. So outside the magnetic field, the loss in kinetic energy is given, potential energy is charge times accelerating PD, which gives it the kinetic energy, that is a half mv squared. So it will be given a velocity v to enter into the magnetic field. For that reason, we just do simple mathematics here. So I multiply this side by 2, it will be twice q times v being equal to m small v squared. Then I multiply both sides by m again, so it will be twice m q v. The other side will be m squared times v squared. Now note that P is momentum, which is m times v. So you are going to notice that twice mqv is equal to the momentum squared. So momentum is going to be the square root of twice mqv. Here the particle has not yet entered into the magnetic field. So we are trying to give it the speed by accelerating it through a PdV. So the loss in potential energy of the electron will be equal to the gain kinetic energy of the electron as it is accelerated towards the magnetic field. The potential difference V is 120 volts. The radius R of the circular arc is 7.4 centimeters. Determine the magnitude B of the magnetic flux density. Now it has entered the magnetic field where it moves in an arc of a circle, so the magnetic force is providing the centripetal force. Therefore, BQV is equal to mv squared over R, which means that mv is equal to BQ times R. One V cancels, so mv is BQR. Remember, mv is momentum, so you can think about momentum as being BQR, but I'm interested in B. So momentum is BQR. Momentum is BQR, and I want the radius. So I want B. So B is going to be equal to the momentum over QR, which momentum is actually the square root of twice mqv over 2r. Over QR. So Q, I will just now substitute, or I will just divide by substituting. So B is going to be the square root of 2 times the mass of the electron, which is 9.11 times 10 power negative 31. The charge is 1.6 times 10 power negative 19. The accelerating PD is given as 120 volts. This is divided by the charge, which is 1.6 times 10 power negative 19, then times the radius, which is 7.4 centimeters, which is 7.4 times 10 power negative 2. Yeah, for long I had not pressed my calculator, so let me press. You have noticed that there seems to be fewer calculations in magnetic fields, because this is the first time I'm pressing the calculator after almost 1 hour. So this is giving me a B as 5.0. You can also press your calculator to verify 5.0 times 10 power negative 4 teslas. The potential difference V in C is increased. The magnetic flux density B remains unchanged. By reference to the momentum of the electron, explain the effect of this increase on the radius r of the path of the electron. So potential difference V is increased. Look at the two equations. Momentum is equal to BQR, and also momentum is equal to the square root of twice mq times V. When the PD is increased, it means the momentum is increased. And when the momentum is increased, automatically the radius must increase. So increasing the PD means a greater momentum. So I will simply say greater momentum. That would increase that means the momentum increases, and from momentum equals to BQR, R is increased, or radius, let me just say full radius increased. The radius is increased, as simple as that. Okay, number 9. A hollow probe is placed near to one end of a current carrying solenoid, as shown in the figure below. So we have a hollow probe, we have a solenoid, which is a coil of many turns. The probe is rotated about the axis XY, I think this is anti-clockwise, and is then held in position so that the hole voltage is maximum. Explain why the hollow probe is made of a thin slice of material. Now here we just have a thin slice of material. Hole voltage VH is equal to BI divided by NTQ. So we are talking about thin slice, that is thickness. So we see that VH is inversely proportional to the thickness in this case. So we shall say hole voltage depends on thickness. Hole voltage depends on the thickness. Hole voltage depends on the thickness of the slice. So the thinner the slice, the larger the hole voltage. So this is very important note. The hole voltage depends on the thickness of the slice. The thinner, I think thinner is double N, I don't know. The thinner the slice, the larger the hole voltage. In order for a consistent measurements of magnetic flux density to be made, the current in the probe must be constant. That is very obvious. That is an obvious observation. You see that VH is depending on the current also. If the current is not constant, that means VH will not be constant, so V will not be a constant value. Therefore, we simply say the hole voltage depends on current in the slice. We are just relying on that expression. VH is directly proportional to the current. So the hole voltage depends on the current. The hole voltage is directly proportional to current. It is directly proportional to B. It is inversely proportional to N and inversely proportional to T and Q. The probe is now rotated through an angle of 360 degrees about the axis of rotation, about XY. So it is otherwise rotating anti-clockwise. At an angle theta equals to 0, the hole voltage is maximum. That is very easy. At any angle theta equals to 0, the hole voltage is maximum. We have seen that VH is equal to BI divided by NTQ. And they are saying when theta is 0, the hole voltage is maximum. That means The component of B is going to be actually B cos theta, because it is cos of theta, which gives us is 1 when theta is 0. So in other words, B here is the component of the magnetic field is B cos theta. That means the angle is measured between the plane of the hollow probe and the magnetic field, and the normal to the magnetic field. The plane of the hollow probe, let's say this is the plane of the hollow probe, and this is the magnetic field from the coil, and I'll use a different color for the normal to the magnetic field. So that is the normal. That's when theta is 0 degrees, when the angle between the normal and the field is 0. That is cos. So we can check what happens to the hole voltage when we are at 90. So at 0 degrees Celsius, that is maximum. Sorry, at 0 degrees, that is maximum. We can check at 90. At 90, that is for theta equals to 90 degrees, VH is going to automatically be 0 because the cos of 90 is 0. So this value here goes to 0. So that will be at 0. Then we can check at 180. When theta is 180 degrees, VH is going to be, the cos of 180 is actually negative 1. So VH is going to be negative Vmax, because it is negative. Cos of 180 is negative 1. So this is going to be, these are 10 small squares representing Vmax. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Vmax in the negative direction, I'll also count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is negative Vmax. Then we can check for theta equals 270 degrees. I think that is VH is equal to 0, because the cos of 270 is 0. And we can check for theta equals to 360 degrees. VH will be equal to Vmax, because the cos of 360 is 1. So 360 degrees, we shall have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we go back to Vmax. So this is going to be a smooth cosine curve, which I'm going to draw. A smooth cosine curve. As simple as that. It's not a straight line, it is actually a smooth curve. So you can draw a better one. Okay, so that is going to be our graph then. Okay. Next, a bar magnet of mass 250 grams is suspended from the free end of the spring, as illustrated here. The magnet hangs so that one pole is near the center of the coil of wire. The coil is connected in series with a resistor and a switch. The switch is open. The magnet is displaced vertically and then allowed to oscillate, with one pole remaining inside the coil. The other pole remains outside the coil. At time t equals to 0, the magnet is oscillating freely. So those are free oscillations. That was when the switch is open. At time t equals to 6.0, the switch in the circuit is closed. The variation with the time t, of course, when the switch is closed, we know that an EMF is going to be induced as the magnet oscillates. The EMF is going to dissipate the energy of the oscillating magnet, and with the time, the oscillations must die out, because energy is dissipated as thermal energy into this resistor here. So the variation with the time t of the vertical displacement y of the magnet is shown here. So you see, for t equals to 0, t equals 6, the amplitude is constant because there is no loss of energy. The oscillations are free. But after 6 seconds, when the switch is closed, you see that the amplitude goes on reducing because the oscillations are no longer free. In simple harmonic motion, we say the oscillations are actually damped. The oscillations are damped. For the oscillating magnet, use data from the figure to calculate two significant figures: the frequency. So to find the frequency, we shall need the period. So from 0, we are now here. I think this is 1, 2, 3, 4, 5, 6. 6. The scale here is 2 divided by 5. I'm finding the scale 2 divided by 5 small squares, that is 0.4. That is the scale, the value of one small square. Now I will multiply this by 6 because there are 6 small squares here representing one complete cycle. So the period will be equal to 0.4 times 6 small squares, which is 2.4. 2.4. So the period is 2.4. So the period is 2.4 seconds. And remember, the frequency is equal to 1 over the period. Period is 1 divided by 2.4. The frequency is 1 divided by 2.4. And this is 0.42. Then the energy of course, this is 0.4167, approximately 0.42. The energy of the oscillations during the time t equals to 0 to time t equals 6.0 seconds. The energy of the oscillations. So because between t equals to 0 and t equals 6, the amplitude is constant, energy here will be the total energy. From simple harmonic motion concepts, total energy is a half m omega squared x naught squared. Or since they gave us here y, I'll use y naught squared. Doesn't change anything. So I'll use y to be consistent with the question. Omega squared times y naught squared, where y naught is the maximum displacement, which is the amplitude. So note that omega is actually omega is 2 pi times f, if you remember this very well from simple harmonic motion. So the energy is going to be a half times the mass. The mass was given as 250 grams. That is the mass. So we just substitute the mass here, that is 250, that is 0.25. To change it to kilograms, where there is omega, I'll put there 2 pi times f, which is 0.42, and this is squared, times the maximum displacement from the graph, which is 1.5. So that is going to be times 1.5. Because it is in centimeters, I'll say times 10 power negative 2, and this is squared. So I check with my calculator. So from my calculator, I'm getting approximately 2.0 times 10 power negative 4, just two significant figures. It could be 1.9 something. So it is 2.0 times 10 power negative 4 joules. You can check. You can check with your calculator. Next, state Faraday's law. State Faraday's law. Of course, Faraday was concerned with the magnitude when Lenz was concerned with the direction. So we know that the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. So magnitude of induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. Then use Faraday's law and energy conservations to explain why the amplitude of the oscillations of the magnet reduces. Why does the amplitude reduce of these oscillations when the switch is closed? You see, when the switch is closed, the amplitude now starts reducing after 6 seconds. That is, the oscillations are being damped. Of course, we know that when as the magnet oscillates in the coil, the coil cuts the magnetic field of the magnet. By Faraday's law, an EMF is induced in the coil. That means thermal energy will be dissipated in this resistor here as a current flows through it. That thermal energy is being derived from the energy of oscillations of the magnet. So the oscillations will now die out, or they will be damped, if I can put it like that. Therefore, we shall simply say that the coil cuts the field of the moving magnet. I need to utilize this space. So the coil cuts the flux or the field of the moving magnet. The moving magnet, inducing an EMF in the coil. Inducing an EMF in the coil. So the induced current, of course, an induced EMF will induce a current. So the induced current in the resistor causes heating. The induced current in the resistor causes heating. It causes heating, and note that this thermal energy has been derived from the energy of oscillations of the magnet. So I will simply say that the thermal energy or the heat energy in the resistor, thermal energy is derived from the energy of oscillations of the magnet which die out. Which will now die out with time. So the induced EMF or the induced current will dissipate thermal energy in the resistor, causing heating. So the thermal energy in the resistor is actually being derived from the energy of oscillations of the magnet. Therefore, the oscillations of the magnet will eventually die out. Okay, next, again explain what is meant by a field of force. We have said a field of force is a region of space where a particle or a body experiences a force, or a region of space where a force is experienced by a particle. So this is a region of space where a force is experienced. Where a force is experienced by a particle. A region of space where a force is experienced by a particle or by a body, that is a field. State the type of field or fields that will give rise to a force acting on a moving uncharged. It is uncharged. We have three fields. We have the gravitational, we have the electric, and we have the magnetic. Whether the particle is moving or not, whether it has charge or not, as long as it has a mass, it is affected by gravitation. Whether the particle is moving or not, as long as it has charge, it is affected by the electric. But it is already affected by gravitational as long as it has mass. For a particle to be affected by the magnetic, it should be moving with its velocity having a component perpendicular to the magnetic field. Therefore, if the particle is not charged but uh, a moving uncharged, so the electric and magnetic do not play a part here if the particle is uncharged. So it is only gravitational here. If the particle is not charged, it is only gravitational which plays a part here, which affects the particle because of its mass. Then a stationary charged particle. If it is stationary, then the magnetic field has no part to play here. Therefore, for a stationary charge, we shall only consider the gravitational because it has mass, gravitational, and because it has charge, although it is stationary, the electric field also comes in play. So it is the gravitational and electric fields. The particle is charged. It is moving at an angle to the field. First of all, it has mass, so the gravitational comes into play. Second, it has charge. Whether it is moving or not, electric comes into play. And thirdly, it is moving at an angle to the field, so the magnetic comes into play. So if it is charged and moving at an angle, the magnetic field comes into play. If it is charged and moving parallel to the magnetic field, still the magnetic field will not come into play. But if it is moving at an angle to the field, then magnetic field comes into play. So all the three will act if the charged particle is moving at an angle. Okay. An electron, mass m and charge negative q, is moving at a speed v. In a vacuum, it enters a region of uniform magnetic field of flux density B, as shown in the figure here. Initially, the electron is moving at right angles to the direction of the magnetic field. Explain why the path of the electron in the magnetic field is an arc, is the arc of a circle. That is a common question. First of all, we have now mentioned that is now part of us that the magnetic force is constant and always normal to the direction of motion or normal to the velocity. So the magnetic force is constant and always. The word always is very important. And always normal to the direction of motion. Or normal to the velocity. So the speed or the kinetic energy is constant. So we say there is no work done. And the magnetic force only provides centripetal force. The magnetic force will only provide the centripetal force. So the magnetic force only provides the centripetal force to cause the particle move in an arc of a circle. Okay, derive an expression in terms of radius, momentum, linear momentum. Okay, and in terms of the radius of the path for the linear momentum of the electron. So we have seen that the magnetic force Fb provides the centripetal force Fc. So I'll simply say that BQV is equal to mv squared over r, where 1v cancels, you remain with the BQ being equal to mv over r. So it means mv, which is the momentum, is going to be bqr. So this is the expression for the momentum. I hope all this R was defined as the radius, B is the magnetic flux density, and Q was the charge. So I don't need to define any term. So that is as easy as that. State Faraday's law, we have simply said the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linkage. The diameter of the cross-section of a long solenoid is 3.2 centimeters as shown in the figure here. A coil C with 85 turns of wire is wound tightly around the center region of the solenoid. The magnetic flux density B in Tesla at the center of the solenoid is given by that expression there. Okay, where I is the current in the solenoid in ampere. Show that for a current I of 2.8 amperes in the solenoid, the magnetic flux linkage of the coil C is 6.0 times 10 power negative 4 Weber. So we simply know that flux linkage or magnetic flux linkage is given by NBA. For those who like basket, that is the easiest way of remembering this. NBA, where N is the number of turns and the number of turns is 85. B is given by pi times 10 power negative 3 times the current, which is 2.8. Then times A, cross-sectional area. They have given us the diameter as 3.2, and we know that area would be equal to pi r squared. The diameter is 3.2, so we divide it by 2. So this would be pi times the radius, which is diameter over 2, which gives us 1.6 in centimeters, times 10 power negative 2 to change it to meters, and it is squared because it's pi r squared. So we are now going to press our calculator just to verify. Of course, since the answer has been given, the substitution will carry the mark, not the final answer. So you must be very careful when you are substituting because the examiner will be looking for what you have missed out. Because if you just write anyhow and say hence equals to this, you will not get the mark. So from my calculator, I've got 6.0 times 10 power negative 4 Weber. That is the flux linkage. Then the current I in the solenoid is reversed in 0.30 seconds. I've underlined reversed. Reversed in this case means it takes a time of 0.3 seconds for the current to switch from one maximum value to another maximum value. Therefore, when we are finding the induced EMF, we have two options. Either we divide the current by 2 or we multiply the resultant EMF by 2 because that would give us the time for just half a cycle. So EMF, the EMF induced is simply going to be N times the change in flux over time, or this will be equal to NBA over time. But this time we shall divide this time by 2 because this time is for the current to reverse from one maximum to another maximum. This will equal to actually 6.0 times 10 power negative 4 over the time is 0. The 2 here will go up, so this will be 0.30 times 2. I am multiplying with these two because the current was reversed. If the current gradually decreased from maximum to a minimum value, or it gradually increased from a minimum value to a maximum value, I wouldn't multiply by 2. But they are saying the current is reversed in that time, meaning that the current swept from one maximum value to another maximum value in this time. So to get the mean EMF, we shall have to multiply the EMF of that time by 2, or we divide the time itself by a half. In other words, I would also just use time as 0.15 seconds. Here I don't multiply by 2 because I've just considered one half of the cycle. So when I press my calculator, of course 6 is divisible by 3, so this is automatically 4.0, because this is 2 times 2, which is 4.0 millivolts, or 4.0 times 10 power negative 3 volts. Then to be 4.0 millivolts. Okay. The current I in the solenoid in B is now varied with the time t as shown here. Use your answer to C to show on the figure the variation with the time t of the EMF induced. We have already seen that EMF is going to be directly proportional to the rate of change of current. When the current does not change, the flux linkage is constant. According to Faraday's law, an EMF is only induced when there is a change in flux linkage. Flux linkage will change when the current is changing. If there's a constant current, then there is no change in the flux linkage. Therefore, the EMF will be directly proportional to the rate at which the current is changing. So let's check. Of course, and like in our previous example, we have seen that when the current is constant, so this is up around 0.3 here, this is 0.3. When the current is constant, there is no EMF induced. So from 0.6 to 1.0, from 1.6 to 0.0, there is no EMF induced. So here EMF is 0, here EMF is 0, here EMF is 0 because the current is constant. So on our graph, I will have to increase the thickness. Let me slightly increase the thickness. On our graph between 0 to 0.3, I think 1, 2, 3, 4, 5, 1, 2.5. 0.3 is there. So here we have a horizontal line. Then we have from 0.6 to 1.0. The current is also constant. So for 1, 2, 3, 4, 5, I think 0.6 is here. Up to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1.0 is here. So I'll draw a horizontal line along the x-axis. Then from 1.6, we see that from 1.6 to 2.0 it is also a horizontal line. So there is no induced EMF here. So 1.6 to 2.0, I'll draw a horizontal line there. Then EMF is directly proportional to the rate of change of current. So we look at the gradient. Let's just look for the gradient. So looking for the gradient, here on the vertical we have, I'm looking at the first part of the graph. The gradients are in opposite directions, so the EMFs will be in opposite directions. The order does not matter. Whether one EMF you put at below the x-axis and another one above, the order doesn't matter. So on the vertical we have here negative, we have 2.8 minus, here we have negative 2.8. Divide by, the difference is from 0.3 to 0.6, that is 0.3, that is the difference. So you have 5.6 over 0.3, that is the gradient for the first part. The second part, we have, I think in the vertical we have the same. For the second part on the vertical we still have 5.6, but the change in time has changed from 1.0 to 0.6, 1.6. which gives us a difference in time of 0.6. So I want you to realize that the first gradient is twice the second gradient, if you notice, because I must multiply this one by 2 to get the first gradient. So I am saying the first gradient is twice the second gradient, which means the EMF of the first gradient must be twice the EMF of the first gradient. I mean the second gradient. EMF here is twice the EMF this side. Therefore, when I'm drawing this, I choose a scale so that the EMF of the first part is twice the EMF of the second part. Let me maybe draw this one at the bottom. So if I use these 10 small squares, the other one I will use 5. If I use this 8, the other one I will use 4 because it is a half. The second EMF is a half of the first one. So let me use 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I will draw a horizontal line here for the EMF. I will increase the size, the thickness. So I will draw a step along between the box here at 0.3. This is at 0.6. So that is the first part. Then I will use 5 boxes for the second part. Remember I said the order doesn't matter. I can draw the first part. I would have put the first part above and the second part below. So that is a very simple graph. But you don't just guess it. You have theory at the back of your mind. You have that theory at the back of your mind. Why do we draw a horizontal line for the EMF? Because the gradient here is constant. That means the EMF is constant and not zero between 0.3 and 0.6. Here we also have a straight line. The EMF is constant but not zero between 1.0 and 1.6. But note that the gradient of the second part here is a half of the gradient of the first part. In fact, to get the first part, I must multiply the second gradient by 2 to get the first gradient. So you have that at the fingertips before plotting the graph. So the graph would take that simple shape. Okay, next, a stiff wire is held horizontally between the poles of a magnet as illustrated here. So we see a stiff wire held horizontally between the poles of a magnet. When a constant current of 6.0 amperes is passed through the wire, there is an additional downward force. Meaning there was already a downward force, but there is an additional downward force on the magnet of 0.060 newtons. On the figure, draw an arrow on the diagram to show the direction of the current in the wire. Explain your answer. When a current of 6.0 amperes is passed through the wire, there is an additional force on the magnet of 0.060 newtons. Meaning there was already a force on the magnet. But then when a current is passed, there is another additional force on the magnet. So on the figure, draw an arrow on the wire to show the direction of the current in the wire. So first of all, before we draw the direction of the wire, we need to think of Fleming's left-hand rule and Newton's third law. So if there is an additional downwards force on the wire, then by Newton's third law, the force on the wire is going to be upwards because there's an additional force on the magnet downwards. So by Newton's third law, I'll just write N3. By Newton's third law, the force on the wire is upwards. The force on the wire is upwards just to balance the force downwards. By Newton's third law, the force on the wire is upwards if there is an addition of this is the force on the magnet downwards. By Newton's third law, the force on the wire is upwards if there is an additional force on the magnet downwards. So two forces must be equal but opposite. So as the wire exerts a force downwards, the magnet exerts a force on the wire upwards. So by Newton's third law, the force on the wire is upwards. And then that is the force on the wire by the magnet is upwards. Then by Fleming's left-hand rule, if now the force on the wire is upwards by Fleming's left-hand rule, then note that the first finger will point from north to south. And we have seen that the force on the wire is upwards by Fleming's left-hand rule. So if the force on the wire is upwards, the thumb, this is now going to be the direction of the thumb. This is the direction of the first finger. You notice that the second finger points in this direction. Therefore, the current in the stiff wire is going to be in this direction. I know people will use Fleming, will answer this question wrongly, because when they see this part here, that when a constant current this is passed through the wire, there's an additional force on the magnet downwards. For them, they will see this as additional force on the wire. It is on the magnet. So by Fleming's left-hand rule, the current is in the direction of left to right. The current will be in the direction of left to right. So that is now the challenge here. Be very careful. If this was the force on the wire, then that would be, your argument would be correct. But since it is the force on the magnet, when this current is passed, there's an additional force, downward force on the magnet, like of 0.08 newtons. That means by Newton's third law, the force on the wire must be upwards to actually balance the additional force downwards. Okay. The constant current 6.0 amperes is now replaced by a low frequency sinusoidal current. The root mean square value of the current is 2.5 amperes. Calculate the difference between the maximum and the minimum forces now acting on the magnet. So the force is given by Bill. Of course, the force on the magnet is equal but opposite to the force on the wire. The force is given by Bill. If I consider the additional force which is experienced on the magnet, which is 0.08 newtons, this will be equal to the magnetic flux density times the current which was flowing there was 6.0. The current is here. The additional current, the current was 6.0. Then times the length of the wire, which we don't have. I will call this one the first equation star. Let's try to find the maximum current. If I find the maximum current for sinusoidal values, maximum current is normally labeled as I naught in alternating current. Remember, I root mean square is I naught over root 2. So maximum current is I root mean square times the root of 2. And this will be equal to the root mean square value, which is 2.5 times root of 2, which is going to be 3. I think this is 3.5. 3.4, 3.5. Let me see. 2.5 times root of 2. That is 3.54 amperes. That is the maximum current that we can have. What force corresponds to this maximum current? Let's check. Using the same expression, the maximum force F max is going to be equal to B times the maximum current, which is 3.54, then times the length of the conductor L. So we can now find, we are going to combine these two equations, this one and the first equation, to get the maximum force. So we are now dividing. I have F max divided by 0.08 is going to be equal to B times 3.54 times L divided by B times 6.0 times L. So all these, most of these have cancelled out. B has cancelled, L has cancelled. So it means the maximum force F max is equal to 3.54 divided by 6.0 times 0.08. I press my calculator. So to two significant figures, I am getting 0.047 newtons as the maximum force. Note that it will sweep from maximum of this force to maximum of and to a minimum of negative 0.04. So calculate the difference between the maximum and the minimum will be negative 0.04, the maximum is positive 0.047. So the difference, or I can say the force varies between uh, 0.0747 newtons upwards to 0.047 newtons downwards. So what is the difference? The difference is simply twice of 0.047. So it can be 2 times 0.047, or the difference can be 0.047 in one direction minus the other in the opposite direction, which is negative, which is 0.047. So these give you the same value. So the difference is going to be 0.094. So the answer here is going to be 0.094 as the difference. Because the current is alternating, it will be maximum on one side positive, maximum or minimum on the other side negative. So the difference is 0.094. Okay. Then again, we should state Faraday's law. Now we are making this familiar with us. So Faraday's law, the force, the magnitude of the induced EMF in a coil. The magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. The magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. This is something easy that you should make part of you. You don't need to spend much time revising such a simple principle. Okay? An alternating current is passed through an air-cooled solenoid. An ion core is inserted into the solenoid and then held stationary within the solenoid. The current in the solenoid is now smaller. Explain why the root mean square value of the current in the solenoid is reduced as a result of inserting the core. Why is it that inserting the core in a solenoid is reducing the root mean square value of current? What happens when we insert the ion core? Of course, inserting the core in the same current, it means there will be a greater rate of change of flux linkage in the core. An EMF is going to be induced in the solenoid, and the EMF induced is going to be greater for the same current when we put a core. Note that according to Lenz's law, the induced EMF always acts as to oppose the change producing it. So if the induced EMF grows bigger in the solenoid, then the induced EMF will oppose the applied EMF, so the current will tend to be smaller, or the induced EMF acts to reduce the current flowing in the solenoid. So this is actually playing around with Lenz's law. We are playing around with Lenz's law. So we shall say that for the same current, the ion core ion core gives a larger rate of change, of flux linkage. For the same current, the ion core gives larger rates of change of flux linkage. Therefore, the induced EMF in the solenoid is going to be greater for the same current. So we are saying induced, I'm writing small things because of the space. So induced EMF, or the EMF induced in the solenoid, is EMF induced in the solenoid. The EMF induced in the solenoid is greater for the same current when there is a core than when there is no core for the same current. And by Lenz's law, the induced EMF opposes the applied EMF. So the current is going to be smaller. So it acts, in other words, it acts to reduce the current. So the current is smaller. So when we put a core, there is a large EMF induced. The induced EMF will now act to reduce the current flowing, because by Lenz's law, the induced EMF is always such as to oppose the change, to cause effects that oppose the change producing it. So in other words, I'm saying the induced EMF acts to reduce the current flowing, because that will be now the change producing it. It acts to reduce the current flowing. That's why now the current in the solenoid is reduced as a result of inserting the core. A large EMF is induced when there is a core. Because there is a large EMF, it acts to oppose the change producing it. So the current flowing in the solenoid was the one producing the EMF. So the current is going to be reduced. Or the EMF produced acts to reduce the current flowing in the core. In the solenoid. Okay, next. Practical transformers are very efficient. However, there are some power losses. State two sources of power loss within a transformer. Those are very easy. We studied these ones. We studied about four sources of power losses. Number one, heating of the core, or heating due to eddy currents in the core. Heating due to eddy currents. Heating due to eddy currents in the core. Number three, we saw hysteresis loss. Hysteresis loss. That is loss due to continuous magnetization and demagnetization, or loss due to the changing magnetic field in the core. Hysteresis loss in the core. Number three, I can add more. Number three here. We have what we call heating due to current in the resistance of the coils. Heating due to current in the resistance of the coils. Heating due to current in the resistance of the coils. And number four, you can also talk about We have talked about heating due to eddy currents in the core. Hysteresis, I think it is hysteresis loss. This is RI, let me write it very well, hysteresis loss. We have also what we call magnetic flux leakage. Energy loss due to magnetic flux leakage. Magnetic flux leakage. People should not confuse flux leakage with flux linkage. So those are some of the four. Possible sources of power loss in a transformer. Okay. Define the Tesla. Define the Tesla. I think this is the longest unit to be defined in magnetic fields. The Tesla. Note that we saw that the force is given by B when the field is at 90 degrees to the conductor, and B was F over IL. B was F over IL, which means the Tesla is going to be a Newton per meter, because in the denominator you have ampere and you have meters. So it is going to be a Newton per ampere per meter. That is the Tesla. Therefore, although the space is very small, we shall still define a Tesla. So the magnetic field is going to be 1 Tesla, or the magnetic field which is producing a force of 1 Newton per meter on a long straight wire carrying a current of 1 ampere. Normal to the magnetic field is going to be 1 Tesla. So we are saying the Tesla is the magnetic field. The magnetic field producing a force of 1 Newton per meter of its length. 1 Newton per meter on a long straight wire or conductor carrying a current of 1 ampere normal to the magnetic field. That is what we call a Tesla. A Tesla is the magnetic field producing a force of 1 Newton per meter on a long straight wire carrying a current of 1 ampere normal to the magnetic field. In other words, a Tesla can be defined as 1 Newton per ampere per meter, that is 1 Tesla, but note that the conductor must be normal to the uniform magnetic field, that is a Tesla. Okay, next, the aluminum frame ABCD of a window measures 85 centimeters by 60 centimeters as shown here. The window is hinged along the edge AB. When the window is closed, the horizontal component of the Earth's magnetic field or flux density that is normal to the window when it is closed. If it is normal to the window when it is closed, it means it will be parallel to the window when it is open. Calculate the magnetic flux through the window. So we know by definition, we have already seen that flux phi is equal to B times A. This will be B is 1.8 times 10 power negative 4 times the cross-sectional area, which is length. This is 85 by 60, that is cross-sectional area. We just change them to meters. So this will be 0.85 times 0.60 to change them to the dimensions into meters. And this is giving me the my calculator So this is giving me 9.18 times 10 power negative 5. In other words, the magnetic flux is 9.18 times 10 power negative 5 Weber. The window is now opened in a time of 0.2 seconds. That means the magnetic flux changes from a maximum to 0 when the window is opened. The magnetic flux changes from maximum to 0. Magnetic flux linkage changes from maximum to 0 when the window is opened. The plane of the window is parallel to the Earth's magnetic field. So the magnetic flux linkage will change from maximum to 0 when the window is opened. Set the change in flux through the window, in the window. Okay. So the change in flux when it is closed, it is max. It is the flux is actually when it is closed, the flux linkage is maximum, and when it is open, the flux linkage is 0. But the magnetic flux is changing from 9.18 to 0. So this will be 9.18 times 10 power negative 5 minus 0 when it is open. So this is going to be 9.18 times 10 power negative 5. That is the change in flux. Because when it is closed, the field is perpendicular to the window. And when it is open, the field is parallel to the window. Calculate the average EMF induced in side CD of the frame. Side CD of the frame, we want to find the average EMF induced. Okay, that is very easy. The EMF induced is equal to N times change in flux over change in time. Because we have just one window, the change in flux or the change in magnetic flux is going to be 9.18 times 10 power negative 5 divided by 0.20. And this means we have assumed that the EMF steadily grows from 0 to maximum or steadily goes to 0. That's why here we don't multiply by 2 because there was no reversing. So here it is steadily goes to 0 when opened. When the window is opened so that the field is parallel to the window, the EMF steadily goes to 0. That's what we have assumed. So here we don't multiply by 2. When I press my calculator, pressing the calculator gives me 4.59 times 10 power negative 14 volts. Is it negative 4? Negative 4. This is negative 4, not negative 14. I'm so short-sighted. So this is negative 4 as the EMF induced. Suggest with a reason whether the EMF calculated in 2 gives rise to a current in the frame A, B, C, D. A, B, C, D. Of course it will because it is a complete circuit and there are no currents in opposite directions, so there is a resultant current. So we can simply say there is an EMF and a complete circuit, so it gives a current. So there is an EMF, there is an EMF and a complete circuit. So it gives rise to a current. If the frame was not complete, if it was open, if it was broken between A, B, C, and D, there will be an EMF and no complete circuit. So if there is no complete circuit, there is no current. But since there is a complete circuit, then there is a current. There is a complete circuit, there is a current. Okay. A charged particle may experience a force. A charged particle may experience a force in an electric field and in a magnetic field. State two differences between the force experienced in the two fields, electric field and the B field or the magnetic field. Of course, we know the force in an electric field is given by QE. The force in a magnetic field is given by BQV. So it means in the magnetic field it depends on the speed, yet in the electric field it can even be stationary. So I will simply say that in the E field, a force is independent. The E field force is independent of speed. In the B field, force is proportional to speed. I've just used that symbol for proportion. In the B field, the force is proportional to the speed. Then number two, in the E field, we saw that a charged particle experiences a force due to the electric field along the field. Yet in the magnetic field, we have been using Fleming's left-hand rule. So in the E field, the force is along the field direction. The force is along the field direction. In other words, if the charge is positive, it moves from high potential to low potential in the direction of the field lines. If the charge is negative, it moves in the opposite direction to the field lines in an electric field. But in a magnetic field, which I'm calling the B field, of course, B field stands for magnetic field, the force is normal to the field. In the magnetic field, the force is normal to the field. And we have been seeing this several times. In the magnetic field, the force is normal to the field. Okay? A proton traveling in a vacuum at this speed, 4.5 times 10 power, I think this is 6, power 6 meters per second, enters a region of a uniform magnetic field of flux density, 0.12 teslas. The path of the proton in the field is a circular arc, as illustrated here. State the direction of the magnetic field. So here we are going to use Fleming's left-hand rule. By Fleming's left-hand rule. It is a proton. The second finger points in that direction of the velocity because it is a positively charged particle. The thumb must point towards the center and it is moving towards the bottom, so the thumb must point downwards. And if you try to make the second finger to point in that direction and the thumb downwards towards you, you notice that the first finger points out of the page, or it points above the page. Therefore, this is going to be out of the plane of the paper. It is not upwards, it is out of the plane of the paper. If you use Fleming's left-hand rule very well. So with your paper on table, you place the second finger in the direction of the proton and the thumb downwards, the first finger points up above the paper, not to the top of the paper, but just upwards. Up. If the paper is on the table, the hand is pointing to the roof. The first finger is pointing to the roof if the paper is on the table. Therefore, it is out of the plane of the paper. Okay, I wish I had internet. I would demonstrate this with an animation. Calculate the radius of the path of the proton in the magnetic field. Of course, when the proton enters the magnetic field, the magnetic force provides the centripetal force. Therefore, we shall simply say that the magnetic force FB provides the centripetal force Fc. Therefore, BQV is equal to mv squared over r. And if that is true, then we shall say that we want r, remember, and make r the subject. 1v has cancelled. So r is going to be mv divided by bq. I now substitute. The magnetic flux density is 0.12. The speed is 4.5 exponent 6. It is a proton whose mass is 1.67 times 10 power negative 27. So I will substitute 1.67 times 10 power negative 27 times the speed, which is 4.5 times 10 power negative 6, divided by the magnetic flux density, which is 0.12 teslas, then times Q, charge of a proton, 1.6 times 10 power negative 19. So I press my calculator. So from my calculator, I get this as 0.39 to two significant figures. You can also press and check. A uniform field is now created in the region as the magnetic field. A uniform electric field is now created in the region, the same region as the magnetic field in the figure that we have seen above, so that the proton passes undeviated through the region of the two fields. On the figure, mark with an arrow labeled E the direction of the electric field. So coming back to the figure here, the force due to the electric field must be downwards. The magnetic field must be downwards. Therefore, the force due to the electric field must be upwards if the particle is to pass through undeviated. The force due to the electric field must be upwards if the particle is to pass through undeviated. And it is a positively charged particle. If the force is upwards, then for a positively charged particle, it experiences a force in the same direction as the field in an electric field. So it means if the force is upwards, then the electric field is going to be in that direction. Therefore, they said draw an arrow, mark with an arrow labeled E the direction of the electric field. So we are saying the electric field is in that direction, so I'll just label the arrow E upwards, vertically upwards. Because it is a proton, it experiences a force in the same direction as the electric field. So the arrow is going to be upwards. Okay. So that one is done. It is upwards. Then calculate the magnitude of the electric field strength. Because now they are balancing, the force due to the magnetic field is equal to the force due to the electric field. So we say that BQV is equal to Q times E, and Q has cancelled. So we want E. So E is going to be B times V. Now substitute. B was given as 0.12 teslas, and the speed was given as 4.5 times 10 power 6. So I press my calculator. So from my calculator, this is giving me 5.4 times 10 power 5 volts per meter. That is from my calculator. Okay, next. Suggest why gravitational forces on the proton have not been considered in the calculations. Of course, we have considered the electric force and the magnetic force, but the proton has a very small mass and the gravitational force is due to this mass. So, of course, we can now predict that the gravitational force is much less than any of those two forces that we have considered. So the gravitational force is much less than the force due to the magnetic field or the force due to the electric field. As simple as that. So a metal is held taut. A metal is held taut between the poles of a permanent magnet, as shown here. A cathode ray oscilloscope is connected between the ends of the wire. The Y plate sensitivity is adjusted to 1.0 millivolts per centimeter. So that is the setting of the vertical, and the time base is 0.5 milliseconds per centimeter. That is the setting of the horizontal. The wire is plugged at its center as shown here. So the wire is plugged at its center, and the trace is seen on the cathode ray oscilloscope like this. Making reference to the laws of electromagnetic induction, that is Lenz's law and Faraday's law, suggests why an EMF is induced in the wire. Of course, here when the wire is plugged, it moves between the poles of the magnet. It is going to be cutting the magnetic field. And by Faraday's law, an EMF must be induced because when there is cutting, there is a change in the magnetic field. Therefore, the wire cuts. We shall say that the vibrating wire cuts the magnetic field. And by Faraday's law, an EMF is induced. An EMF is induced when there is a change or when there is cutting of the flux. There is the wire cuts the magnetic field, and in accordance to Faraday's law, an EMF is induced whenever there is cutting of flux or whenever there is a change in flux. So that is why there is an EMF. Secondly, why the EMF is alternating. Now we pull out Lenz's law. Lenz proposes that the induced EMF is always such as to oppose the change causing it. So it means as the wire moves, it keeps changing direction, and therefore the EMF also changes direction. So by Lenz's law, the EMF opposes. I will use the word oppose. Although it causes effects to oppose, it opposes the change causing it. So as the direction of movement changes, so does the EMF. So as the direction of movement changes, the direction of the EMF also changes. Okay, so that is why it is alternating. As the direction of movement changes, the direction of the EMF also changes. So alternating. Okay. Use the figure 7.2 that we have seen and the CRO settings to determine the equation representing the induced EMF. So let's come back here. First of all, we need to get the vertical. So this is at the center here, and this is also at the center almost. So I will just count the number of small squares on the vertical. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and a half. 14 and a half and another half up, those are 15. So on the vertical we have 15 squares representing peak to peak. So it is 15 times the setting there. Each small square on the vertical is going to be 1/5. So it means this is 3 centimeters. So peak to peak is 3 centimeters. Peak to peak is 3 centimeters. From one peak to another peak, it is 3 centimeters. And remember, each centimeter on the vertical is representing 1.0 millivolts. We want the amplitude now. So the amplitude is going to be half of this. So the amplitude on the vertical, I'll call it Y naught. Okay, the amplitude is going to be equal to a half of 3, which is 1.5 centimeters times 1.0 millivolts per centimeter. So the amplitude is going to be 1.5 millivolts. That's the amplitude. Then I will check the period. So I'm starting, say, from this point here. It is actually in the center, I think. It is actually in the center. If not here, it is here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So those are 30 small squares between one center and another one. So I've just chosen corresponding points. You can verify. So on the horizontal axis for the time setting, we have 30 small squares. 30, each small square is 1/5 from this labeling here. There are 5 small squares in 1 centimeter. So that is 6 centimeters from this trough to the other trough. 6 centimeters. That is one cycle, of course. So the period is going to be equal to 6 centimeters times the time-based setting, which is 0.5 milliseconds per centimeter. So the period is going to be 3 milliseconds. So now we can go and solve this equation. So we have seen that the amplitude was 1.5 millivolts, as I have showed you there. And we have seen that the period is actually 3 times 10 power negative 3 in seconds. This is 1.5 times 10 power negative 3 in volts, if necessary anyway. But if not necessary, we can still leave it like that. Note that the general equation here, the general equation is going, because it is sinusoidal, the current or the EMF is sinusoidal, so I will say EMF, or I will use X is equal to X naught sine omega t. So I need omega. So omega is 2 pi over t. And 2 pi, this is going to be 2 pi over the period, which is 3 times 10 power negative 3. I press my calculator. From my calculator, I get 2090 radians per second. So I know that X naught is the amplitude, which is 1.5 millivolts, and omega is now 2090 radians per second. So I'll write the equation as X naught, which is 1.5 times 10 power negative 3 sine 2090 times t. So the equation required is going to be X equals to 1.5 times 10 power negative 3 sine 2090 times t. That is the equation we are talking about here. So note that 4 marks is too much. Therefore, you have to be careful in obtaining these quantities that we have obtained earlier on here. I obtained this quantity to guide me for V. I had to find it for one complete cycle from here up to this point here. So you must be very careful. All those can also be put as part of the working when you are trying to come up with the values. You can still include them. Next, the poles of a horseshoe magnet. The poles of a horseshoe magnet measures 5 centimeters by 2.4 as shown here. The uniform magnetic flux density between the poles of the magnet is 89 milliteslas. Outside the regions of the poles, the magnetic field is 0. A stiff copper wire is connected to a sensitive ammeter of resistance 0.12 ohms. A student moves the wire at a constant speed of 1.8 meters per second between the poles in the direction parallel to the faces of the poles. Okay. So since it is part of the faces of the poles, so they are cutting perpendicular. Calculate the magnetic flux between the poles of the magnet. So flux of phi is equal to B times A, where when we substitute, B is 89 times 10 power negative 3. Cross-sectional area will be the cross-section area through which the conductor is cutting. That will be 5.0 times 10 power negative 2, then times 22.4 times 10 power negative 2. When I press my calculator, 89, 5 times 2.4. So this gives me to three significant figures, 1.07 times 10 power negative 4 Weber. Use your answer in A to determine for the wire moving between the poles of the magnet the EMF induced. So this is the flux inside the poles. So outside it is going to be 0. So the change in flux is going to be that one. So the change in flux is going to be 1.07 times 10 power negative 4 Weber. That is the change in flux because outside flux is 0. So the EMF is going to be the change in flux with the time. This takes, we don't have the time here, but of course we have the speed. So the change in flux is known, but we don't have the time. But we know that area over time is actually speed times length. The rate of change of area is equal to the speed times the length. In other words, area over time is speed times length, which means time can be area over speed times length. That is one. Time can be area over speed times. Alternatively, since we are given since the wire is going to be moving through a vertical distance and we have the speed with which it is moving, then we can find the time. That will be even the easiest way. Let me use that one as the easiest way because it will be very direct. It will be very, very direct. So as the wire is moved, the time is going to be the distance through which it moves. That is 2.4 times 10 power negative 2 in the vertical. It is moving vertically and it is moving at a speed of 1.8 meters per second. So I'm now just going to substitute here. The EMF is going to be the change in flux, which is 1.07 times 10 power negative 4 divided by the time, which is This will be now 2.4 times 10 power negative 2. When I divide, the 1.8 goes up, so this will be times 1.8. So I'll just press my calculator here. 1.07 exponent negative 4 times 1.8 divided by 2.4 exponent negative 2. So this is giving me 8.025 or 8.03 times 10 power negative 3. Therefore, the EMF is approximately 8.0 times 10 power negative 3 in volts. Show that the reading on the ammeter is approximately 70 milliamperes. So that the reading on the ammeter is approximately 70 milliamperes. So reading on the ammeter, that is current. Current will be equal to V over R, or the EMF over R. So this will be EMF over R, which will be 8.0 times 10 power negative 3 divided by the resistance, which was given as 0.12 ohms, and this is giving me 0.8 divided by 0.12, that is 66.7 times 10 power negative 3 amperes, which is actually going to be 70 milliamperes when you round off, because 10 power negative 3 is in milli. When you write this to the nearest significant figure, it will be 70 milliamperes, as simple as that. By reference to Lenz's law, a force acts on the wire to oppose the motion of the wire. The student who moved the wire between the poles of the magnet claims not to have felt this force. Explain quantitatively. When the question says quantitatively, you need to quote a value. So let's first find the force on the wire and see if it can be felt. The force on the wire is given by Bill. I think the force on the wire is given by Bill. Let's say the force on wire is given by Bill, and this is going to be B is 89 times 10 power negative 3. The current is 70 milliamperes, that is 70 times 10 power negative 3. And the length of the wire in the magnetic field is the length of the poles from this point to this point here, that is 5 centimeters. So this will be times 5.0 times 10 power negative 2. And when I press my calculator, pressing the calculator, the force is 3 times 10 power negative 4 newtons. So this force is too small to be felt. This force is too small to be felt. That force is too small to be felt. Therefore, the student's claim is making sense, because 3 times 10 power negative 4 newtons is too small to be felt. It's too small to be felt. Okay, next. Electrons are moving through a vacuum in a narrow beam. The electrons have speed v, so they are negatively charged. Electrons enter a region of uniform magnetic field of flux density B. Initially, the electrons are traveling at right angles before they enter the field, of course. The path of a single electron has been indicated here. The electrons follow a curved path in the magnetic field. A uniform electric field of field strength E is now applied to the same region as the magnetic field. The electrons now pass undeviated through the region of the two fields. Gravitational effects may be neglected. Derive the relation between V, E, and B for the electrons not to be deflected. Explain your working. So for the electrons not to be deflected, we know that the force due to the electric field is equal to the force. Okay, let me just write it in words. For the electrons not to be deflected, the force due to the E field is equal and opposite. Is equal and opposite to the force due to the magnetic field, or due to the B field. When I write B field, that is the magnetic field. So what does this imply? This implies that BQV is equal to Q times E. And if Q cancels out, it means V is equal to E over B. As simple as that. So the force due to the electric field is equal and opposite to the force due to the magnetic field. When we equate the two equations, we should be able to get such an expression. An alpha particle has speed v and approaches the region of the two fields along the same path as the electron. Of course, we know an alpha particle is a helium nucleus, He42. The charge is positive 2e, yet for the electron it is e. The mass is 4u, yet for the electron is 9, exactly 1 over 18, 40 times u. Describe and explain the path of the alpha particle as it passes through the region of the two fields. Note that although the alpha particle has a higher mass and a higher charge, in this expression here, mass and charge do not exist. They don't appear here. Therefore, it will still undergo no deviation since the charge and mass are not involved in the equation. So, still no deviation of the alpha particle, no deviation of the alpha particle since the charge and mass are not involved in the equation. The mass and the charge are not involved in the equation. V equals to E over B. So it will still also be undeviated to just pass through. Okay, next. Positive ions are traveling through a vacuum in a narrow beam. Ions enter a region of a uniform magnetic field of flux density B and are deflected in a semicircular arc as shown here. Okay, so the particles are deflected in that semicircular arc. The ions, traveling with the speed 1.4 times 10 power 5 meters per second, are detected at a fixed detector when the diameter of the arc is 12.8 centimeters. By reference to the figure, state the direction of the magnetic field. So here we pull out Fleming's left-hand rule. By Fleming's left-hand rule, pull out your left hand. The second finger points in the direction of the positive ions. Normally, the thumb must point towards the center of the circular path, because the center should be somewhere here, because in all cases the force is always acting towards the center. So the thumb at this point here, the thumb is pointing towards the center. And when you do that, you will notice that when you place the second finger pointing this side and forcing the thumb to point towards the center, the first finger is pointing to the page. So we simply say that the field is into the plane of the paper. The field is into the plane of the paper. The field is into the plane of the paper. Okay, the ions have mass 20U and charge 1.6 exponent negative 19. Show that the magnetic flux density is 0.4 teslas. Note that when the particles enter the magnetic field, the magnetic force provides the centripetal force. That is, BQV is equal to mv squared over r. So making V the subject, one V has cancelled, making V the subject. B is going to be equal to M, which is 20U, and 1U is 1.66 times 10 power negative 27. Then times V, which is 1.40 times 10 power, V was 1.40 times 10 power 5, divide by R, which is the radius. The radius, they gave us the diameter as 12.8, so the radius is 6.4 times 10 power negative 2. Then times B, times B. B is what we want to find, so it is times, we have R times Q. And the Q is 1.6 times 10 power negative 19. I press my calculator to verify. 20 1.66 exponent negative 27 times 1.4 exponent 5 divided by 6.4 exponent negative 2 times 1.6 exponent negative 19. It is actually giving me 0.454 teslas to three significant figures. Ions of mass 22U, the other one was 20U. The same charge and speed as those in A are also present in the beam. On the figure, sketch the path of these ions in the magnetic field of magnetic flux density 0.4. So we know that from the formula here, if we are seeing that the radius is equal to, making radius the subject, is mv over bq. So they are saying v is, they have the field is B is the same, the charge is the same, and the speed is the same. So it means R is directly proportional to M. Now these ones have a larger mass, therefore they should have a larger radius. So they told us to sketch. So I'll sketch a new path which has a higher diameter like this one than this one here. So I will sketch a new path with a higher diameter than that one, that is as easy as that. Because they said sketch the path of these ions in the magnetic field. Because they have a greater mass, they have a larger diameter. In order to detect these ions at the fixed detector, the magnetic flux density is changed. The magnetic flux density is going to be changed. Capture the new magnetic flux density. So we have already seen that BQV is equal to mv squared. We have already seen that BQV is mv squared over R. In other words, B times Q is equal to mv squared, mv over R when I cancel out one V. For the first case, we have already seen that when B is 0.454 times the charge Q, our mass was 20 U times the velocity V over the radius R. We want them to reach the same point. We want them to have the same diameter, so we are fixing R. That's number one, but we are adjusting B. So the second case, we have B times the same charges, because they have the same charge, should be equal to, the new mass is 22U times the same speed over, we want the same radius so that they are detected at the detector. So this is my second equation, this was my first equation. So I'm dividing the two equations. So I have BQ divided by 0.454 times Q being equal to 22U times V divided by R divided by, I'm dividing so I get the reciprocal, so it will be R over 20U times V. So a lot of these quantities are cancelling out, So Q has cancelled, V has cancelled, R has cancelled, U has cancelled. So in other words, I remain with B over 0.454 being equal to 20, 2 over 20, and which means I make B the subject, and making B the subject, I just press my calculator, 22 divided by 20 times 0.45. And this is giving me 0.499 to three significant figures. A uniform magnetic field of flux of constant flux density. I want to do much today. A uniform magnetic field has a constant flux density B. A straight wire of fixed length carries a current I at an angle theta to the magnetic field. So theta is the angle between the conductor and the magnetic field. That means when I resolve vertically, it will be sine. The current I in the wire is changed, keeping the angle theta constant. On the figure, sketch a graph to show the variation with the current I of the force. It is a straight wire, so the force on the straight wire is going to be B sine theta. And they are saying the angle is kept constant, so it means the force is directly proportional to the current, and that is a straight line. So here we shall just do a straight line. Just put the ruler and draw a straight line because the current is directly proportional to the force. In our second part, the angle theta between the wire and the magnetic field is now varied. Note that force is equal to B sine theta. The current, all these ones are kept constant, so the force is going to be directly proportional to the sine of theta. We can check. When theta is 0, F is going to be 0. So theta equals to 0, F is 0. And when theta equals to 30 degrees, I think the force is going to be a half of the maximum, because when theta equals to 90 degrees, the force is F max. So maximum force is at 90 degrees. And if this is maximum, this is corresponding to maximum force, at 30 it should be half. At 30 it should be half. The force is half of maximum. So I'll only consider 3 points. This one, and for maximum force. And this will be a smooth curve. To be a smooth curve, which stops at 90 degrees. So it will be a smooth curve at 90 degrees. Let me rub off this so that people do not get confused. It is not a straight line. It is a smooth curve. It is a very smooth curve up to 90. Okay. A uniform magnetic field is directed at right angles to the rectangular surface PQRS of a slice of a conducting material as shown in the figure below. So we have a uniform magnetic field which is vertically downwards, and the direction of movement of the electrons is from this side. So it means the current is going the other way around, because the current is always in the opposite direction to the movement of the electrons. Electrons moving towards the side SR enter the slice of the conducting material. Since the electrons are coming from this side and the current is the other side, so you will notice that the PD is a potential difference is created between these two faces in the opposite faces, explaining why initially the electrons do not travel in straight lines across the slice. So initially, the electrons will not move in a straight line because there is a force on them due to the magnetic field which is greater. So they are moved towards one particular end. But then with the time, they can now move to in a straight line when the force due to the magnetic field balances with the force due to the electric field, due to the electric field that has been created. Okay. So what does this mean? The electrons inertia do not move in a straight line because there is a force. There is a force on these electrons due to the magnetic field. And the force is normal to the direction of motion of these electrons. So we are saying there is a force on an electron due to the magnetic field. Maybe yellow this color is not good for people. There is a force on an electron due to the magnetic field, and the force is normal. And the force is normal to the magnetic field and direction of the electron. And the force is normal to the magnetic field and the direction of the electron as given by Fleming's left hand rule. So there is no way they would travel in a straight line, because Fleming's left hand rule is predicting that the force is acting normal to the direction. The force is acting normal to the magnetic field and the direction of the electron. So they can't move in a straight line. Explain to which sides PS or QR the electrons tend to move. So if we want to tell the direction of the electrons, we can still use the right hand rule directly without reversing the second finger. Using the right hand rule, put the first finger onto the paper if the paper is on your table, and make the second finger point in the direction of the electrons. And when you do that, you see that the thumb is pointing towards QR. That is by Fleming's right hand rule. But we're not supposed to use the Fleming's right hand rule, by the way. We're supposed to use Fleming's left hand rule to tell the direction of the force. So by the left hand rule, make the first finger to point onto the paper, and instead of making the second finger to point in the direction of motion of the electrons, you reverse the second finger to point in the opposite direction to that of the electrons. Still, the thumb points towards QR. You must have tried this. Make the first finger point onto the paper, because the diagram is on paper and the paper is on the table. Instead of making the second finger to point in the direction of motion of the electrons, you reverse it to point in the opposite direction. That is, you rotate your hand in 180 degrees. So the thumb is pointing towards QR. And therefore, by Fleming's left hand rule, because it's acceptable to use Fleming's left hand rule here, by Fleming's left hand rule, the electrons move towards QR. So you can't just say electrons move towards QR and you get 2 marks. No, you must verify Fleming's left hand rule. Okay, so having used Fleming's left hand rule, then we can now proceed. A constant current is maintained in a long straight vertical wire. A hollow probe is positioned. Remember, a hollow probe is used to measure magnetic flux density. A hollow probe is positioned at distance r from the center of the wire, as shown here. Okay, so we have a hollow probe positioned there, and I think it can be rotated along the axis XY. Explain why when the whole probe is rotated about the horizontal axis xy, the whole voltage varies between a maximum positive value and a maximum negative value. In other words, the whole voltage changes sign and varies in magnitude. So we can think of the formula for whole voltage first. We know that VH, the whole voltage VH, is given by BI over NTQ. So it means it is depending on B, where B is the angle between the probe and, B is the component of the magnetic field which is normal, the plane of the whole probe. So it is actually depending on the component of the magnetic flux density. So VH is depending on the angle between the plane of the probe and the magnetic field. So I will simply say VH, that is the whole voltage, depends on the angle between the plane of the probe and the magnetic field. The plane of the probe and the magnetic field. So VH is going to be, this will be maximum when the angle is maybe 0 if we consider cos, between the plane of the probe and the magnetic field. So if the angle is 0, that will be, if theta is the angle between the plane and the magnetic field, it means resolving to the vertical, it will be sine. So when theta is 90 degrees, then to be maximum. So it means V is maximum, VH is maximum when the plane and the probe, when the plane and the B field or the magnetic field and the magnetic field are normal to each other. VH is going to be maximum. VH is maximum. Let me write this in full for simplicity. VH is maximum when the plane and the B field are normal to each other. VH will be maximum and it will be 0. And 0 when the plane and the B field are parallel. Of course, it will change direction because the angle changes also direction. The cutting changes direction. So that is why it will sweep from maximum positive value to maximum negative value. So there will be change in direction. So we are simply looking at B here. B depends on the angle the field makes with the plane of the probe or with the conductor. The maximum whole voltage VH is measured at distances R, different distances R. Data VH and the corresponding values of R are shown here. So they have given us data. It is thought that VH and R are related by an expression of the form VH is equal to K over R, where K is a constant. Without drawing a graph, use data from the figure to suggest whether the expression is valid. So let's try to see if the expression is valid. So VH is equal to K over R, where K is a constant. Let's verify if K is a constant really. So we shall be finding VH times R to see if it is equal to what? To a constant. So we shall check. For the first set, I will have VH is 0.290 times R, which is 1.0. This is giving me 0.290 to 3 significant figures. When I check the second one is 0.190 times 2.0, it is 1.5. I'm just trying to check to see if VH times R is a constant. So this is times 1.5. And when I press my calculator, this is 0.285, three significant figures. I can also check the third one, 0.140 times 2.0. Three significant figures, this is automatically 0.280. So you notice that when I consider three significant figures, VH times R is not a constant. So the statement is not valid. So to three or even to two significant figures. So two significant figures, this would be 0.29, this would be 0.29, but this would be 0.28. So I'll say to two significant figures, VH times R is not a constant. So the statement is not valid. So not valid. That is one. Alternatively, to one significant figure, VH times R is approximately equal to 0.3, which is a what? A constant. So if you take to one significant figure here, you will say, so the statement is valid. The expression is valid. If I take more significant figures, they are different, so it's not valid. If I consider one significant figure, it is the same, so we can say VH times R is a constant, so the statement is valid. So the choice will depend on you, whether you want it to be valid or not valid. Both answers will be correct. This is another alternative, so you can't have both of them at the same time. Okay, a graph showing the variation with 1 over R of VH is plotted. State the feature. So you are seeing that VH is equal to K over 1 over R. So if we plot VH against 1 over R, that is a straight line. So VH is directly proportional to 1 over R. Therefore, we shall have a straight line. As 1 over R increases, VH is increasing. So this will be a straight line passing through the origin. Straight line passing through the origin. Of course, it will be different if we plot R against VH, because VH is inversely proportional to R alone, but is directly proportional to 1 over R. If it was VH against R alone, that would be a different graph. It may not pass through the origin. Okay. The hollow probe in A is now replaced with a small coil of wire connected to a sensitive voltmeter. The coil is arranged so that its plane is normal to the magnetic field of the wire. State Faraday's law of electromagnetic induction and hence explain why the voltmeter indicates a zero reading. Of course, the first part is telling us to state Faraday's law. So we know Faraday's law, the magnitude of the induced EMF in the coil in a coil is directly proportional to the rate of change of magnetic flux linkage. So the magnitude of the induced EMF in a coil is directly proportional to the rate of change of magnetic flux linkage. So they are saying, and hence explain why the voltmeter indicates a zero reading. The hollow probe in a coil is now replaced with a small coil of wire connected to a sensitive voltmeter. So let's come back here. The current flowing here is actually direct current. So there is a constant field. So the flux of the coil does not change, hence there is no induced EMF. So because we have a direct current, there is a constant field. So there is a constant magnetic field. There's a constant field, so flux linkage is not of the coil does not change. Flux linkage of the coil does not change. Flux linkage of the coil does not change, hence no induced EMF. Because we have a direct current flowing into the wire, as you can see here, showed by this arrow here. There's direct current flowing through the wire, so the magnetic field around the wire is constant, so there will be no induced EMF unless something is done. So what should we do to induce an EMF there? I think it's the next question. State 3 different ways in which an EMF may be induced in the coil. How shall we induce an EMF in that coil above? There are several ways. Because it is carrying direct current, we can vary the current, increase it or decrease it, even though it is direct. We can switch off this current or switch it on. We can replace the current with alternating current. We can rotate the coil around the current carrying wire. All those ones will induce an EMF in the coil. So we are saying vary the current in the wire, vary the current in the wire, vary the current in the wire. That is, you can switch on or off. Switch on or off the current. You can use alternating current, use AC current or alternating current. You can rotate the coil. You can move the coil towards or away from the wire. Move the coil towards or away from the wire. Okay. Negatively charged particles are moving through a vacuum in a parallel beam. The particles have speed v. The particles enter a region of uniform magnetic field of flux density 930 microteslas. Initially, the particles are traveling at right angles to the magnetic field. The path of a single particle is shown here. The negatively charged particles follow a curved path of radius 7.9 centimeters in the magnetic field. A uniform electric field is then applied in the same region as the magnetic field. For an electric field of strength that 12 kilovolts per meter, the particles are undeviated as they pass through the region of the fields. On the figure, mark with an arrow the direction of the electric field. So we have a uniform electric field of flux density that the particles are being showed here. And of course, the particles are negatively charged. So for a negatively charged particle, using Fleming's left-hand rule, the thumb must point upwards. The second finger must point in the opposite direction to the particle. So the second finger is pointing that direction. The thumb must point upwards because the particle is moving upwards. So if you make the second finger to point upwards, the thumb to point upwards, with the second finger pointing in the opposite direction to the negatively charged particle, you notice that the field is out of the page. So the magnetic field is out of the page. Then we can check, because the force due to the magnetic field is upwards. The force due to the magnetic field is upwards. It is an electron where it experiences a force in the opposite direction to the field. So the force due to the electric field must be downwards. Because it is an electron and it experiences a force due to the electric field in the opposite direction to the field, this part must be positively charged, and the top must be negative so that the field is in that direction. and the electron experiences a force in the opposite direction. Therefore, the question was, on the figure, mark with an arrow the direction of the electric field. So the direction of the electric field is upwards because the force on the electron is downwards. So the arrow should be pointing upwards. I will just take one arrow which is pointing upwards. The direction of the electric field is upwards because the force on the electron is downwards due to the electric field. Okay. On figure 7.1, mark with an arrow the direction of the electric field. That one we have finished. Calculate for the negatively charged particle the speed. So when it enters across the field, then they say the particle passes undeviated. That means the force due to the magnetic field is balancing with the force due to the electric field. So we say that BQV is equal to Q times E, making V the subject. V is going to be equal to, because Q has cancelled, to be E over B, which when I substitute, E is 12 times 10 power 3, 12 kilovolts per meter. And the magnetic flux density is 930 microteslas, so that is 930 times 10 power negative 6. So I press my calculator. So from my calculator, I have 1.3 times 10 power 7 meters per second. Okay, calculate for the negatively charged particle the ratio charge to mass, charge over mass. So still, when the particle enters, if it was to enter a uniform magnetic field, then the magnetic force provides the centripetal force. So that means BQV is equal to mv squared over r. So V cancels. So Q over M is equal to, in the denominator, because I've divided by M, so we remain with the V in the denominator over B times R, I guess. So we now substitute. So Q over M is going to be V, which is 1.3 times 10 power 7 divided by B, which is 930 times 10 power 10 power negative 6, then times, this is looking ugly, times R, which R is the radius. What was the radius? 7.9 centimeters. The radius is 7.9 centimeters, so this will be times 7.9 times 10 power negative 2. So I press my calculator. So from my calculator, I have 1.8 times 10 power 11 as the charge to mass ratio. Next, a rectangular slice of aluminium has sides of length 65 millimeters, 50 millimeters, and 0.10 millimeters, as shown in the figure here. Some of the corners of the slice are labeled. The current I, 3.8 amperes, is normal to the faces R, S, X, Y. So current is flowing in that direction. You should now be noting that the EMF, the PD is created between this end and the other behind end there. In non-aluminium, the number of free electrons per unit volume is that. So this is N. A uniform magnetic field of flux density B equal to 0.13 teslas is normal to face QRYZ of this aluminium slice in the direction Q to P. So the field is in the direction Q to P, that is downwards. A whole voltage VH is developed across the slice and is given by the expression VH is equal to that. Use the figure to state the magnitude of the distance t, the magnitude of the distance t. Of course, from the figure, t is the thickness and t is 0.10. So this is 0.10 millimeters. Calculate the Hall voltage of, calculate the magnitude of the Hall voltage. So we just substitute in the formula. VH is going to be B, where B is 0.13 times current. Current is 3.8. Divide by a number density, that is 6.0 times 10 power 28. Thickness is 0.1 times 10 power negative 3 to change it to meters. The charge, these are electrons, so I will say 1.6 times 10 power negative 19. 1.6 times 10 power negative 19. I press my calculator. So from my calculator, I'm getting 5.1 times 10 power negative 7. You can always verify because human error in pressing the calculator cannot always be. It could cause a deviation in the answers. So you can always check by pressing the calculator. Okay, next. A coil of insulated wire is wound on a copper core as illustrated here. Okay, we have a coil in copper core as you can see here. An alternating current is passed through the coil. The heating effect of the current in the coil is negligible. Explain why the temperature of the core rises. If the heating effect in the coil is negligible, explain why the temperature of the core rises. Now note that we have alternating current, which creates a changing magnetic field in the core. Changing magnetic field in the core also induces different magnitudes of current in the core. So an EMF is induced in the core. So different currents, which we shall call eddy currents, are also induced in the core. These eddy currents cause a heating of the core. So we are saying the non-uniform magnetic flux in the core is changing because of the alternating current. So alternating current causes a changing magnetic field in the core. So, and it is not uniform, so I will simply say the non-uniform magnetic flux in the core is changing. And by Faraday's law, this induces different EMFs. Because the magnetic flux is non-uniform, this induces different EMFs in different parts, calling them EMFs in different parts of the core. In different parts of the core. So the induced EMF, of course, the induced EMFs will now give rise to eddy currents. The induced EMFs generate eddy currents. Induced EMFs generate eddy currents. in the core. Generates eddy currents in the core, which give rise to heating of the core. So this is easy to explain. When I insert a core between the coil of a of wire, this is alternating current. Alternating current will give rise to a changing magnetic field in the core. There will be different magnetic fields in the core, so there will be different magnetic flux in the core. The changing magnetic field by Faraday's law induces EMFs. The EMFs will be different on different parts of the core because the magnetic field is not uniform on different parts. So because they are different EMFs, they induce different currents on different parts of the core, and the different currents are what we are calling eddy currents. The eddy currents dissipate energy in the core from I squared R because there is a resistance in the core. The eddy currents dissipate energy in the core, which causes the heating of the core. That is that part of the question. Next, two hollow tubes of equal length hang vertically as shown here. One tube is made of plastic and the other of aluminium. So this is plastic. So if the magnet moves through it, there is no problem. The magnet, nothing happens to it anyway. Because this plastic is not a conductor. Two similar bar magnets A and B are held above the tube and then released simultaneously, that is at almost the same time. The magnets do not touch the sides of the tubes. Explain why magnet B takes much longer than A to fall through the tube. That one is simple common sense. Plastic is not a conductor, aluminium tube is a conductor. As the magnet falls, the aluminium tube will be cutting the magnetic field of the magnet. An EMF or EMFs are going to be induced in the aluminium tube, which EMFs will give rise to currents or eddy currents in the aluminium tube, which causes or dissipates the energy of motion of the magnet. So we are saying as magnets fall, as the magnet falls, as the magnet falls, the aluminium tube cuts the magnetic flux. So different EMFs are going to be induced in accordance with Faraday's law. So by Faraday's law, different EMFs. I think I'm now tired. By Faraday's law, different EMFs, and thus eddy currents are induced. In the aluminium tube. Different EMFs and thus eddy currents are induced in the, of course, different EMFs give to different currents, which we are calling eddy currents. So the eddy currents cause heating of the tube. The eddy currents cause heating the tube. The eddy currents cause heating of the tube with the energy. This thermal energy is being derived from the falling magnet. The eddy currents cause heating of the tube with the energy derived from the falling magnet. The energy derived from the falling magnet. With the energy derived from the falling magnet, so the magnet B has a smaller acceleration, maybe it even reaches terminal velocity. So the magnet B has a smaller acceleration which will be less than that of gravity. Yet in magnet A, it will have a higher, this one will accelerate due to gravity, and this one will have an acceleration less than gravity because of its energy being converted into thermal energy. So we are saying, so magnet B has smaller acceleration, which is less than acceleration due to gravity. Oh, by the way, it could also reach terminal velocity. Of course, when it reaches terminal velocity, the acceleration becomes zero. So it takes long or reaches terminal velocity. Alternatively, yes. Instead of talking about the energy being converted or the energy of the eddy currents being derived from the falling magnet, the eddy currents may produce a magnetic field that opposes the motion of the magnet. Still, this makes B to have an acceleration less than gravity. After eddy currents are produced, instead of causing heating, I can simply say the eddy currents produce a magnetic field also. The eddy currents will produce a magnetic field that opposes motion of the magnet in accordance with Lenz's law. That opposes the motion of the magnet, so magnet B has acceleration less than that of gravity. It will have acceleration less than that of gravity, yet magnet A is moving with that acceleration due to gravity. As simple as that. Next. A magnetic field of flux density B is normal to face PQRS of a slice of a conducting material as shown here. State what is represented by the symbol N. Remember, N was number density of charge carriers. N was number density of charge carriers. Charge density, that is number density of charge carriers or number of charge carriers per unit volume. Number of charge carriers per unit volume, or number density of charge carriers, or number of free electrons per unit volume. Free electrons per unit volume. Number density of charge carriers or number density of free electrons. They should be free electrons because charge carriers must be free. So number density of charge carriers or number density of free electrons or number of free electrons per unit volume. That is number of free electrons per unit volume or number per unit volume of charge carriers number of free electrons per unit volume, number of free electrons per unit volume, number of free electrons per unit volume. That is another alternative. The symbol T represents the length of one side of the slice. Use letters from figure to identify T. T is the thickness. T is the thickness. It can be Px, it can be Qy, it can be Rz. So I can say Px, or it can be Qy, or it can be Rz. That is the thickness. T is this distance here. In general, the whole voltage produced in a slice of a metal is small, very small. For a slice of the same dimensions with the same current and magnetic flux density, the whole voltage produced in a semiconductor material is much larger. Suggest and explain why. Semiconductor, we know for a semiconductor, VH from the expression given there, VH is inversely proportional to N. So I will simply say VH is inversely proportional to N. VH is inversely proportional to N, and for semiconductor, N is very, very small. For semiconductor, N is much smaller. N is much smaller than for metals. So that is self-explanatory. If VH is inversely proportional to N, and yet for semiconductor, N is much smaller than for metals, then that means VH is going to be larger for semiconductors. In some semiconductor materials, electrons are mainly responsible for conduction. In other semiconducting materials, the holes are mainly responsible for conduction. So if electrons are responsible for conduction and the holes are responsible for conduction, then they are supposed to be deflected in the same direction in a magnetic field. But of course, concepts of holes are in the band theory, the BT, the band theory, which is now no longer part of the syllabus. The band theory is no longer part of the syllabus, but I will just, for completeness, give this. Suggest and explain the difference, if any, that conduction by electrons or by holes will have on the hole voltage. So because conduction is by electrons or holes, it means these are supposed to be deflected on the same side or in the same direction in a magnetic field. So we shall say magnetic field, the magnetic field would deflect holes and electrons in the same direction. The magnetic field will deflect holes and electrons in the same direction. And because holes are negatively charged, yet the holes are positively charged, yet the electrons are negatively charged. So because electrons are negatively charged, and holes are positive. So it must be confusing as to why they are deflected by the magnetic field in the same direction. Conduction is by either holes or the negative or the electrons. So if conduction is by either holes or electrons, then they are supposed to be deflected on the same side in the magnetic field. And since the holes and the electrons have opposite charges, then the whole voltage I will have opposite polarity. So we shall say VH has opposite polarity or opposite signs. So VH has opposite polarity or opposite signs. So that is this is simply for completeness, but I said the band, this is in the band theory, which is normally this is no longer out of the within the syllabus. The band theory where we talk about holes is not part of the syllabus. However, if conduction is either by holes or electrons, then the magnetic field should deflect them on the same side or in the same direction. Okay, we are almost done. I wanted the video to be 4 hours. Two coils P and Q are placed close to one another as shown here. The current in coil P is constant. Of course, if it is constant, the magnetic flux linkage is constant, so there is no induced EMF. An iron rod is inserted into coil P. Explain why during the time the rod is moving, there is a reading on the voltmeter connected to coil Q. Of course, when the rod is moving, it is cutting the magnetic field. There is a change in magnetic field. Whenever there is a change in magnetic field by Faraday's law, an EMF is induced. So we can say the moving iron rod. The moving iron rod changes flux density, or it changes the field. The moving iron rod changes the field of the flux density, and by Fleming's left-hand rule, not Fleming's left-hand rule, by Faraday's law. And by Faraday's law, change of flux in coil Q will induce an EMF in this coil. By Faraday's law, change of flux in coil Q, change of flux or field in coil Q causes an induced EMF in it. So the moving iron rod causes changes the flux density or field in the first coil. And by Faraday's law, this change, of course, this changing flux is linked to the second coil. So the change of flux in coil Q will cause an induced EMF in this coil, as simple as that. The current in coil P is now varied as shown here. So this is the variation of current. Note that the induced EMF is going to be directly proportional to the rate of change of this current. Between somehow far from or around T1 to T2, the current is constant, so here the EMF is going to be 0. But there is a small time interval here where the current sweeps from one maximum value to another value. Here the gradient is constant, but is very sharp, it is very high, So the current jumps to a very high peak, to a very high constant value, and then it becomes 0. The induced EMF becomes 0. So in our next part, they are telling us to draw on the figure, show the variation with the time of the reading of the voltmeter connected to a coil Q. So in this part here, where the current is constant, the EMF is going to be 0. In this part here, where the current is increasing but constant, the EMF is going to be a certain constant value. But then here the gradient is positive and here the gradient is negative and very high. So this jumps to a very high value. Around here it jumps to a very high sharp value and it becomes constant. So then it moves back to 0. So we shall consider this at a value close to T1, the EMF is constant because the gradient of the line was constant, so I will draw a horizontal line. But just very close to T1, it jumps to a negative value because the gradient changes. So there will be a sharp, there will be a narrow spike in one particular direction near T1. So this will jump to a certain value in the opposite direction, because the gradient was high, so it jumps to a high value. And then it comes back to 0. So there will be a spike there. There will be a spike there in that direction, and then it becomes 0. So that is the simple graph. That is the simple graph. This spike should be going to a higher value than the current in the first part, because the gradient, as you can see from the graph, this gradient here is very high. The gradient in this region here, around T1, you see the line is almost vertical, but not very vertical. So there will be a spike in one particular direction. So I'll draw a spike here close to T1, which jumps to a high value. It goes to a high value. So that, I don't know why it is hard for me to draw a nice spike. Okay, so this is going to be how the voltage, the reading varies. It jumps to a very high value close to T1, then it comes back to 0. So for you, I may have exaggerated it because I'm drawing this on paper, but this time interval here is supposed to be very narrow. It is supposed to be extremely narrow. So you need to depict that. Okay, so I have very few minutes remaining, and I can conclude with the last question, number 9. A particle of charge positive Q mass m is traveling at a constant speed 1.6 exponent 5. The particle enters a uniform magnetic field of flux density that, as shown here, the magnetic field direction is perpendicular to the initial velocity of the particle and perpendicular to and out of the plane of the paper. A uniform electric field is applied in the same region as the magnetic field, so that the particle passes undeviated through the field. State and explain the direction of the electric field. So if it passes undeviated, yet the magnetic field was out of the paper, the first finger should be pointing above your paper. If the paper is on the table, the particle is positive, the second finger should be pointing in the same direction as the particle, so the thumb is pointing downwards. So it means the force due to the magnetic field is downwards, so the force due to the electric field should be upwards. State and explain the direction of the electric field. Because the force on the charged particle is upwards, it is always towards lower potential, so this is negative. The force on a positive particle is towards lower potential, so this is going to be positive. So that means the field is upwards. So we shall say the electric field is up of the page. The electric field is up the page. Because the direction of the force must be opposite to the force due to the magnetic field. Direction of electric force must be opposite to the magnetic force. And by Fleming's left-hand rule, I'll just write FLHR, Fleming's left-hand rule. The force due to the magnetic field is downwards, or down the page. The force FB is down the page. So I'm not saying into the page, it is just down the page. You see it is down of the page, it is towards the bottom of the page. by Fleming's left-hand rule. That means the force due to electric field must act in the opposite direction. And yet this is a charged particle which is positive. It always experiences the force in the opposite direction to the field. I mean the same direction as the field. So the field must be upwards. Calculate the magnitude of the electric field strength. So since the force due to the electric field is now balancing the force due to the magnetic field, so we shall say QE is equal to BQV. In that case, Q has cancelled, so E is going to be equal to B times V. When we substitute, this will be 9.7 times 10 power negative 2 times 1.6 times 10 power 5. That was, I think, the speed. 9.7 exponent 2, 1.6 exponent 5. Then when I press my calculator, so from my calculator, this is 1.55 times 10 power 4, or approximately 1.6 times 10 power 4 volts per meter. Part C, the electric field is now removed so that the positively charged particle follows a curved path in the magnetic field. The path is arc of radius 4 centimeters. So if it now follows a curved path, then the magnetic force provides the centripetal force. So I'll simply say that BQV is equal to mv squared over r. When I make Q over m the subject, so Q over m, because V has cancelled, Q over m is going to be equal to V over B times R. So the ratio Q over m is going to be V, which is 1.6 times 10 power 5 from above, and B, which is 9.7 times 10 power negative 2 times R, which was 4 centimeters, 4 times 10 power negative 2. So this must give me the ratio. I'll just press my calculator. So by pressing my calculator, this is 4.12 times 10 power 7 coulombs per kilogram. The particle has charge 3e, where is the elementary charge. Use the answer in C to determine the mass in U of the particle. So since charge to mass ratio is that, so it means mass is going to be the ratio. Sorry, mass is going to be the charge over that ratio. So this will be 3. The charge is 3e, 3 times 1.6 times 10 power negative 19 divided by the ratio, which is 4.12 times 10 power 7. And this gives me, just divide. So this is giving 1.16 times 10 power negative 26 in kilograms. And when I divide this by 1.16 times 10 power negative 26 in kilograms, divide this by 1.66 times 10 power negative 27 to change it into unified atomic mass units. This to one significant figure, it is giving me 7.0 U. So the answer here is going to be 7.0 U. State the particle is a nucleus of an atom, so it is a nucleus, so X is going to be 7.0 U, and this one is going to be 3 because the charge is 3e. So number of protons, that is going to be 3. Number of neutrons will be 7 minus 3, which is equal to 4. As simple as that. So let us start from this question next time. We shall start from page 189. Let's start from the page 189 next time. I hope you have enjoyed this. Make sure you have a hard copy, a printed copy, so that you can always follow. Use a ruler where necessary, because I may not always use a ruler. And paper 2 will also be uploaded soon. past paper questions are ready, but I want to upload them when I'm starting to answer them or to record them. So the past paper questions for paper 2 for all the new topics, all topics excluding electric fields which was removed are also ready. I'll be uploading them soon. Thank you and have a very good day. Bye bye.